haven't already found it, we've got some light breakfast out front, some pastries and coffee. There's also some vegetarian, vegan options over on the table where the coffee is, if you didn't locate those. Restrooms are just on the other side of this wall, and there is a door here for an emergency exit, but of course we'd ask that you go out the back door and go around to the restrooms to avoid disrupting the presenter. We do have some splinter rooms available if anybody needs to duck out for a meeting. We do have a couple of them reserved at a couple of different times, but in general they're available. There's one just outside the doors to your left here. There's a smaller one that's back over here, and then we also have one on the second floor just outside the elevator. We have a smoking area out here, which is outside this wall here. And then, of course, we have exits back over here, but of course Melissa would like you not to use that one unless there's a fire or something. Also, we have an exit here, exits out there, and then exits out these doors to your right as well. In case of a fire, our muster point is back in the parking lot back here, and you'll see that here. So here's our meeting room here, and our muster point would be back here in case of an emergency. If you are a non-U.S. person, make sure that you filled out an international visitor form and that you have an international visitor badge. If you are a non-U.S. person and you haven't done those two things, please check back in with our registration desk and they'll get you fixed up. Also, you'll want to make sure you turn in your badges at the end of each day. Presenters, make sure, again, we do have international visitors, so please make sure your presentation adheres to export control and ITAR regulations. Some technical stuff. We do have a wireless network. It's SWI guest. You don't have to have any authorization. You just connect to it, and you should be good to go. A lot of you already found the power on the table. You just press the little thing, and you get some power there on the table in front of you. Of course, most people have cell phones these days, but if you need a phone, we have some phones out in the lobby, and our admins can help you with that. If you need to print something, there are some computers out in the lobby as well. Last thing I want to point out is we do have a large group. We have a microphone here in the middle of the room. If you do need to ask a question, please get up and use that microphone. For our remote presenters, I don't know if they can hear me or we're having some trouble with our system, but we ask our remote presenters to, if they have a question, to ask their question through the chat feature, and then Jason will get that question to us and we can get it answered. Meals, I'll give you an update each day on meals, but again, we do have some continental breakfast available outside. We're also having lunch brought in from Jason's Deli, and again, we've tried to accommodate dietary restrictions for vegan, vegetarian, gluten-free, and so forth. And then, of course, we'll have some snacks available in the afternoon as well. Lastly, I want to thank our sponsors, OER and MathWorks and AdaCore. We couldn't put this event on. There are, as you can imagine, expenses putting something like this. We're small and formal. We try to keep costs low, but they're still our costs, and our sponsors, we're just so thankful for them, and been great sponsors for us over the years, including this year. So thanks to our sponsors. With that, I'm going to turn it over to Dave McComas for our CFS morning.
Okay, well, yep. All right, well, thanks everybody for coming. I'm really glad to see the good turnout. And my name is Dave McComas, and I've been at Goddard for many, many years. And I've been a proponent of the CFS since kind of day one, I think. And anyway, and who's new to this, or who's not experienced with the CFS? Maybe I should ask that way. So, okay, well, good. I'll do. Feel free. You'll get to meet everybody engaged in the CFS, the team members, and the multiple. It's across the multiple centers. So please interact with us during the breaks as well. This isn't a tutorial. This is just going to be more of an introduction to get us, kind of set the stage for today. And again, I'd like to first thank Southwest and Melissa for then helping out everybody. And I'm sorry, I already lost the name here, but thank you very much for all the support and the help. And again, our sponsors, and also the steering committee, or the planning committee, that was also a joint effort of many people. So these things don't just happen, magically. So it's a lot of effort that goes in. So, and then also, we didn't plan any breaks for a CFS day, so feel free to get up for the half day. It is, we are squeezing it into a half day, and there's a lot to go over, so we'll just keep it rolling. So one thing we have is terminology. So CFS is an evolution, and so there's always been confusion on terminology, and over the last year, I've been trying to kind of hone it in a little bit, and it's getting there. So it's got multi-layers. So it's a open source, when I'm calling these first two layers framework, and actually you see 4, but it's actually 2 APIs. So we got a platform implementation, and that consists of the operating system abstraction and the hardware abstraction. Not all the devices, but the processor board abstraction. And then that has an API, and on top of that is a Core Flight Executive, which provides services. And then that has an API for the applications. So those bottom 2 layers is, we call them a framework now, so that way we have something, then that's where the apps sit on. And what happened was we have released these incrementally, as we'll see shortly. But then when we started to release apps, we had to call it something. So then we said, oh, let's call it the Core Flight System. But now there's just multiple apps. So there's no one Core Flight System. There's just a distribution that uses the framework with apps. So hopefully that made sense. And so the framework has, tools and a runtime environment for the applications. And we're also supporting both NASA Class A and B artifacts. And basically what we're kind of in the stage now is trying to grow the community. So, and also to get it more enabled as a user contribution. So this is kind of the evolution. I'll just go through this kind of quickly. But so before 2007, I was going to ask you, is anybody younger than 25? Do we have any college? Oh, there's 1, 2, 3. Oh, wow. So this almost started when you were in kindergarten. Oh. Okay, that's fine. Well, I'll keep talking. So back, we did a Core Flight Executive. We actually open sourced and released the OSAL layer. And there's Alan Cudmore, who's the author. So we have some people here that are back from the early days, usually the ones with gray hair. And we used some project-independent funding. And we also, what we did was we had a large heritage of many missions at Goddard, science missions. And we took a step back and we actually did a heritage analysis that where's the commonality and where's the variability and how can we architect this to accommodate it. So it was a very structured effort. Even though we didn't have the funding to implement everything at once, it was an upfront design effort. So then we started because of funding, we leveraged a lot of projects. So that's why you'll see an evolution. So then we went to the moon in 2007 and the LRO used the OSAL and the CFE. So at that point we had the bottom 2 layers. And they had some apps that they adapted, but they weren't the reusable apps. And then between 2008 and 2014, we released the CFE as open source. Then Goddard, most of it was under global precipitation measurement. We developed 12 applications that went open source. And at the same time, Johnson did a Class A certification on the Airing 653. And I can't remember when Morpheus was in there. That was also a big player, but that really helped as well. 12. So that was another good testimony of a project, and that was down at Johnson where they just used the CFE, and it was really beneficial. So then in 2014, we actually got a whole bunch of together, the NASA centers, and we actually said, okay, let's form, and this is kind of brand new, and we're still in this new territory. We said, let's manage this as a multi-center effort, and no longer, so it kind of, in one sense, left Goddard. The chair is still out of Goddard, but we have a board that's made up of all the NASA centers or whoever wants to participate. And so then then the apps went open source in January 2015, and then with this board in place, we now started managing the components. But it did get a little fuzzy. It wasn't all smooth sailing, so some of the apps went back under the board control, and now we've made an effort. The Goddard apps now are being pulled back, and you'll see a presentation on this by Beth Timmons, she's now the Goddard component lead. So the board really is concentrating on the framework, which is important. And so then we held our first workshop, and then basically from 16 to 18, where we are now, we're kind of in our adolescence. We've done a bunch of releases. 6.5, the stars, they're all open source. 6.6, I'll just say it now. It's still in the process of becoming open source. So apologize for the slowness. We've Patent Office Council wanted us to go back through the process, and it's been kind of laborious. But it is available for all government projects. And then the other nice thing, and this is where the community started happening. Johnson gave back, they made some nice tools and additional apps, and we're starting to see that really grow, and we want to continue that growth. And now we're back at the workshop. So just kind of from an analysis point of view, because the evolution is important, and I ran across this. This was, and I won't go through the words because we're actually going to be a little tight on my intro. So, but it was useful to say, this was from a Microsoft architecture document I was reading once. And has, what are the three things that are, kind of vying for the quality attributes of a system? And you got your user, you've got your business, and then you got your system, which is the technical product. And when I started thinking about the CFS and those evolutionary steps, it really did make me, I thought it was kind of interesting to take a look at each of these three real quickly. And then, so if we look at the user, we've gone from, this was a branch at Goddard, was trying to make our better, more cost-effective. Now we've got an international community. So we've got, trouble tickets or comments or help desk requests from, literally internationally. So that's put a lot of strain on, the infrastructure of what we've set up to date. So we're working on it. I mean, I realize that I'm just trying to be kind of transparent as well. So because it's not all where we want it to be. We realize we're a government organization trying to do things that really haven't been done before. And a lot of them have different quality attribute priorities. Universities want ease, everybody wants ease of deployment. At Goddard, we just go down the hall and, talk to Alan. Say, help. And a lot of people still call Alan. And then like DOD, they've expressed an interest, but security wasn't one of our top quality attributes at Goddard. So we really haven't gone down that path. And doesn't mean we don't want to. It's just that we haven't, because when we initially did that system. And again, we want the users, the bigger group wants more system engineering documentation. Yeah, Jonathan.
Yeah, so like IOR, we have access to this blacked up security analysis tool. So we're going to put all the code through there and then see what the reports are. And then put in tickets for things that we need to fix. So we'll go through that security process.
So the comment was, so it was Mike Aguilar from the NASA Engineering Safety Commission, NESC. I got to get my acronym right. Has a tool set that they can run for security analysis, which will be really helpful.
And no cost.
And no cost, even the biggest thing.
Yeah, I was just curious,
Sure.
because it is so useful for us, and because you formulated CFS prior to the basic asset protection plan requirements for NASA, what are your challenges going forward?
I'm not actually sure, what challenges they're placing or what's being levied on us.
Part of it is the framework itself, going through these tools, make sure you don't have the little security holes that close like buffer or those kind of things. But the real protection is on the front end, and then whatever the mission requires, maybe a crypto in the comm interface or other type of encryption that doors into the vehicle. So that's something that missions usually decide. There's nothing specific to the framework for that, but there may be applications that address that.
In a more general sense, NASA right now, through some of the funding that I'm putting together, is building access to some of these tools that implement some of the scanning that you need to meet. In essence, nobody knows how to meet those requirements, except maybe have a checkbox type thing that you analyze and guarantee. Originally, our legal department was going to come up with a check sheet that the original engineer was going to check off saying, yeah, my software is safe, and then we were going to hand that back to them. And we're not wild about that. So we're trying to get, in essence, a portal. I don't know if many of you are familiar with a group called Swamp, where they have an open source portal where you can run static code analysis on the system. We're trying to put one of those within the NASA firewall.
I'm not going to repeat what you just said, so.
Okay, I'll start at the very beginning. What it amounts to is nobody can get a hold of these tools because they're expensive. And so what we wanted to do is build a portal where you can upload or run a scan using these tools. Primarily right now, it's just to see what we get. And then if we can build a report out from these tools that the legal department will sign off on if we run the scan, we can start to meet some of these security and quality and ownership issues that are coming across the board. But it was all a matter of how do you implement something like that that's rapid enough to support an engineering discipline. And that's the direction we're going. That's just getting put together, and I'm going to use CFE CFS as one of the prototypes that runs through the system.
Thank you. Great. Thanks. Any other questions? Okay. Well, and I'm in the honor respect of time, I'll kind of go quick. So then there's the frustration of open source project, and our government, obviously 6.6 is still not open source, so I think people can relate. Then you look at the systems perspective, it's actually, it's been quite well in certain, so what's scaled, so now we got the base is increasing, and the business is increasing, but now, so I just picked out 2 examples. So Scheduler app, that's, now Johnson's done a time-triggered Ethernet with the Scheduler app, and that's been a really, to me, that's been a really good testament that the design of actually putting a scheduler as an app versus lowering the layers. And then the API stability, it's been very stable since LRO, since 2007. What's not scaled so well is table generation tools, and this, you guys probably all felt this pain who's ever used it. So, we have our local Goddard ground systems, and we depend on the command telemetry definition reports, and so we haven't had, that's one area where we didn't scale the tools to meet the user demands. And then we have build test scripts that we run on each release, but they're unique to our ground system. I mean, it's not a Goddard custom, but it's not, you have to pay to get it. And again, our lack of documentation in the right areas. It's got a lot of documentation. Some of it's just missing in some of the systems area. And then some ongoing conversations, binary versus text table. I think one of the Goddard apps in the queue is a text-based stored command app. So, I mean, there's things going on. And the binary, if you got the table generation tools scaling, they kind of work hand in hand. File systems and how we use them, and that's ongoing. And you'll see some more about the electronic data sheets, but getting a tool chain to support a single definition of command and telemetry. Now, from a business, so we've also expanded. So I don't. People are aware of the Lunar Orbiting Platform Gateway. I can never say that well. But CFS is actually in the requirements for that, so that's great. And I think that's in part because of the interoperability. That was one of our high priority requirements, the plug-and-play architecture. Now, unsustainable and inefficient is a little harsh, but I mean, help desk is borrowed. We do tax some local. We tax some local projects, but we don't tax it. It's not like a common funding source. And part of the thing, we're missing some of the product cycle. So Goddard, we evolved it over, let's say we launch every 3-4 years, we have a mission. Now that we have this big community, we really should be leveraging the experience of people gathering in their product cycles. And that'd be, we're just not doing that to the level I think we could. And we're getting, so we still don't have an online distribution catalog. I got another slide on that. So an area that I really wanted to get up and have it by this time. And then, our mailing list is our primary Q&A form. It'd be nice to have. We've talked about Stack Overflow. And I'll say it now because at the end of my next slide, I want to have a splinter on Wednesday at lunch. So if anybody wants to talk about programmatics, there's a conference room in 201 upstairs. So we could talk. I have another slide in the other deck. But, I'd love to get some feedback. And then you got the government challenges. We're still working through those. So from a business, though, we are expanding even more. So this was just announced last week. I don't know if everybody's familiar with this, but there's NASA announced the U.S. companies that are eligible to bid on delivery services for lunar payloads. And I don't know. I only highlighted the 3 I'm aware of. I know these 3 use the CFS. Yeah, there's more. Actually, if people know, I'd love to get to find out of this list. So it's kind of neat that this whole new initiative in the commercialization, actually that's a theme of the workshop this year, commercialize to space, and so we're kind of right in there in the mix. And then here's the other big business world is the CubeSat world. I mean, it's exploded because of NASA's launch initiative, and this is just a map showing where the selections and what's launched and the manifestations. So it's really really. And then here's some, I don't know if anybody else, if you're not on this list, anybody has a CFS launch coming up. Definitely want to hear about it. So we actually had a low year at Goddard, or NASA. I mean, we had the Atlas, which didn't really, it used the OSAL. It didn't use the CFE. That was an instrument at Goddard. But they did actually use a CFS in a simulator.
He'll use it next time.
Next time, yeah, we've we sent them this proper training. And then it's on, and Johns Hopkins Solar Pro Plus, and then here a bunch of launches coming up. Actually, I think Jedi's tomorrow. I think, is it? Yeah. So yeah, all right. And that's a NASA instrument or a Goddard instrument going on the space station. So thank you all for being here. It's really about, so the whole goal of this, you'll see the morning's a little loose. We come in and try to get a lot of different perspectives from the NASA community for this half day. And but it is really about engagement. So I really want everybody to ask a lot of questions. You got a lot of people here that have been experience-based, and we really want to get the feedback. And I won't go through this, so I'll just jump right into the next presentation. I think you got copies of this. So if everybody is, I know I don't want to take away from anybody else's time. So I'm going to jump into the program management.
Sorry, can I?
Sure, oh, of course.
I just wanted to ask when we show this link of quality.
Mm-hmm.
Is it the open source version or the in-house version of TFS? Because I thought that it kind of got used to.
No, it's the open source version. Any project is free to make tweaks to the open source, but the baseline is the open source.
There's not much selfishness in the open source. There's a lot of built open source that is not like the current core CFS.
Right.
It's not folded up around the asset version service.
Yeah. Right. Yeah, and actually, most of those are probably all 6.5. The ones coming out because that's been frozen. They
didn't change, so it doesn't matter.
It's not a state change. It is a doc.
There's bug fixes.
The lawyers.
Not
Oh. Okay. Was there another question?
Yeah, I was just kind of wondering, previously you said that you guys had mostly done unit testing on your Goddard stuff that you had in-house. Do you open up the unit testing framework so that people can show them the unit test?
Yeah. Yeah, so the question was, would you unit testing on Goddard systems? And this might be a terminology, and sorry if I misspoke. On the Goddard ground system, that's what we call build testing. So that's against the functional requirements at a black box level. The unit tests are run on a desktop, and they use a unit test framework that is open source. And all those unit tests themselves are open source. And there are some changes now. That's where 6.6 would really help to get out, because I think there are some problems with 6.5 and some of the hooks. So that's frustrating that that's not out there. Maybe because it's not flight code, maybe we can just get that out. Separate open source release.
They were mentioning that it's very high coverage in the unit.
Yes.
Because part of it, because what JC did for 5-day cert, they went through and it's like, the code coverage is complete with exceptions are all well documented why you couldn't test that particular part.
Okay, thank you. So I'm going to go a little bit, just briefly, product management, and what I'm calling product management, the framework and Goddard components. And this is just an introduction. We'll get more on some of these areas. And then so my hat is with a program manager hat, even though I'm not really a program, I don't have a budget, so I'm a program influencer. So I don't really, but that's fine. So my hat, and you'll hear, so we got a lot of people working on these things, but what I'm trying to do, my goal in fiscal 2019 is so we can get some of this folded back in. I mean, that's really, so there might be multiple efforts working on multi-core, but we're working to get a couple core things, and that's part of the lesson I've learned over the evolution. You can't pick everything. Let's fix get a couple of the key things in and prioritize. So over 19, it's going to be multi-core, then the electronic data sheets and command data dictionary you'll hear, there's multiple efforts going on there. And now, Johnson and Goddard are having bi-weekly meetings, and we'll get, even if the projects go and do what they need to do to meet their deadlines, we'll have an effort that's at the program level of how to fold this back into the framework and get the tool chain. But that takes a dedicated, different mindset. And we also have the Simulink interface layer, which Steve Lentine will be talking about later in these, where that actually has forked as well, but the Goddard path has done an open source release, and that lets code that's generated from that MathWorks Simulink models run as a CFS application. And then also training, that's an area. We have a lot of pieces around, but it really would be nice to get a consolidated somewhere effort that people can go to. So from a program overview, this is the Goddard roles. So I'm the program influencer. The lead architect is Jonathan Wilmot, who's been already talking to, and then Alan Cudmore is our platform development lead. And we actually are going to have, so we had people leave at the end of last year, which was one of our slowdown with 6.6 as well. So unfortunately, we lost our CCB chair and product lead from the Goddard side. And I wish this were a week later. We could, I think we'll have an announcement within a week, so that'll be good. So we're hoping we have a full-time Goddard person dedicated. Jonathan and I have been kind of sharing the chairing, but we really haven't been thinking of the product and the schedule and getting deliverables. We've just been kind of holding it together. So that's exciting. And during the course of the year, one of the big, Beth Timmons will be presenting. It's really been helpful to have her as a dedicated Goddard component lead. So she's thinking about the apps and any tools that Goddard develops and really focusing on maturing them and getting them under a CM. They kind of migrated out the AIM server, and it got a little fuzzy of who was owning them. But they'll just be, Goddard will be just like anybody else, where Jonathan released some tools and apps. We'll just have our, and then the framework will be the shared component. And then we have a test lead who is not here, but Walt Molesky is the one who runs all the release tests on the build level at Goddard. And Goddard has a couple in-house, which is good because we're leveraging these for the PACE is actually doing multi-core work. Both of these are doing multi-core work. So that's been a big help. And they're also using, some of the tools that Steve will be talking about. And then we have Johnson, the Advanced Exploration Systems. I don't know, they're our primary. They've been very helpful over the last several years in providing support funding. So that's really what's kept us alive, and that's been wonderful. And Pam will be speaking. She's the software lead. And then we have, there's also, I don't know who's aware of the Lunar Catalyst program, and the nice thing, that's been in effect, and actually those 3 companies I highlighted before, the nice thing there is that's a partnership with 3 companies that NASA can, where if we put resources to help that company, they also have to help NASA. So it's a nice way, and we've been leveraging some of that to get some of the advancement in some of the tools. Oh, yeah, okay, that's fine. And then we have the configuration board and the active members. I didn't list the people, just the centers. But, okay. Next one, yeah, thanks. So, well, that's good. It had a little animation, so I was trying to hide some of the complexity. It's not that's all right, that's okay. That's okay. Doesn't matter. I probably wouldn't have done the sequence. So this is the product model I've been promoting, and this is where I love to have a splinter and keep getting feedback. It's kind of more like a Linux model, even though it may not look like it. So we got the NASA group here, and then we have, they should publish, we got our framework, and the framework, again, is the service and the platforms. And we haven't really published specs. We have an app developer's guide, but, eventually if we the tool chain with the electronic data sheets, we should have a spec of saying this is how you deliver an app to be integrated into the framework. So basically then we have component suppliers who can supply anything that plugs into the framework. And now I get to do where are the oohs and ahs, you know what's coming. So then the supplier, and then we have distributors. And in a sense, and I have a slide with what I would call 4 distributions to date. That's people that put it together that then make it available as a working unit. I mean, that's been part of the problem of adaptability is, you got everybody pulling CFE, they know different apps, and say, how do I get this to work as a system? And then right now we have a NASA website that's very static and controlled. I've been trying to work, and again, it's a lot of the borrowed things. We like the price tag of free, so that doesn't always get things. But we need the commercial, there's a center Struck organization that's hosted a website for us, but unfortunately we got hacked in June or July and shut down. Now we're on the process of getting it back up, but one of the goals was to really get the good list of applications and platforms, and it could be more of a marketplace that's a little more dynamic than a government website. but we're not quite there yet. And then this, I won't go through this. This was just a chart showing, trying to identify everything the CCB should control. And then here's a list of, this was on the website, which is not there right now. So this is what I call identified distribution. So we actually have a Goddard one, and we got to get clear our message. We have a guy at Goddard who put the CFE 6.5 and then pulled the apps together and put it out on NASA Git. And that will build, and you can build it on your desktop. The disadvantage, it really doesn't have a ground system with it. It has the Python tool where you can just send 1s and 2s commands. So, but it is a really helpful way of seeing the make system and the build. The part we haven't done is we haven't advertised, and I'm just coming, you know, I haven't said, is this the where we want people to put tickets in the public space for changes to our apps? We've got to really get that communication model down. And then Jonathan's created a CFS Framework 101. They may not consider it a distribution, but in a way it is. It's a VM with the CFS running in it, and has some good tutorials. So that's actually a really good place to start. NASA, IVB, and I think there's a talk later today on this. They've got this is using Cosmos, an open source Ball aerospace ground system running with CFS and 42, it's the open source dynamic simulator. And then I've actually got a little side project myself called OpenSat Kit, and that's basically Cosmos and CFS too, and that's free on the side. But it gives you both of those. My goal of mine was to just have a training platform, where NOS 3 is really engineered for the life cycle of the mission, and they actually have it where you can put hardware in a loop. So it's an impressive system. So I'm not going to go through these in the interest of time. So the state of the CCB, we are up. I won't go through all the bullets. I got 3 slides on this. This is from another presentation. But basically, we are functional now. We're running. We're working on 6.7. We're going through the tickets. And like I said, hopefully we'll have an announcement of a lead within a week or two. I guess the only other part is, you know, so TAM is running these biweekly CFS meetings as well, and I almost look at that as more of a technical steering meeting. So before the CCB was, you know, doing everything, and that's not really the job of a CCB, and we need to, as we get more, we'll keep working on getting more structure. So we're acting chair, and Chris Knight, thank you, Chris, is taking over the Ames responsibility when, because it took us a while to get started back up. And the other important thing here is, so 6.6, we are actually pursuing the Apache 2.0 license. And unfortunately, I can't give you any more detail than that, other than we're pursuing it. Especially in the international partnerships, the NOSA license has some things that aren't, you know, it'd be much easier to go with Apache 2.0. So 6.7, I think I've already mentioned that we're working on it. And things we're still working out, you know, how many platforms should NASA really control and test on? So those are the kind of questions that we really got to nail down. But again, I'm kind of, so we'll have a talk. So this is more introductory. So I've already mentioned Beth will be talking on the Goddard components. The multi-core effort, Alan has a presentation on that, and it's mostly Alan and John. It's being done in multi-center. So when I say lead again, this is from a perspective of getting it back into the framework. It doesn't mean there's not efforts that are being led by other groups. And electronic data sheets, Jonathan has another meeting, and I've had some work under the Catalyst book that I'm helping with, and that's where I'm going to help coordinate these back into the framework. And there's a lot going on here. So this is going to be an exciting year for that, I think. And then the Simulink interface layer, I've already mentioned, Steve, so I won't go through that. And then training, I say vacant lead. If anybody wants to coordinate all the training packages that are out there, but there's a lot of pieces that are out there that really could be pulled together. And again, if people come to the Splinter, that's really, it's going to be on Wednesday at lunch. I'll make sure it gets announced, and that's really all I had. So then we almost stayed on time. So I don't know if any other follow-up questions from the program. I think next up is Tam. So
Hey, one question.
Sure.
What happened to the training with the drone from Odyssey? Was that on? Cause You went fast. Was that on your list?
That was not on my list, and I think they're here, so oh, all right. Is there,
Well, I probably
okay.
should address that. So I funded that, but, unfortunately, I didn't keep it up to date. So, I funded that effort, and it was a really good thing, but, and what I have found that when you fund a lot of things like this, you also have to maintain them, and, unfortunately, that one took sort of a lower priority for me, so it's available, but it's rather outdated.
Is it available though as open source?
I'm not sure, I have to check. I thought it was.
I haven't seen it, at least it's not released.
Okay,
If
okay.
it's open source, it might have the license on it, but it's not released.
Yeah, I'll check on it. I thought that one did make it through.
Any other questions? All right, thanks. Next up is Sam No from the Advanced Exploration Systems.
Can everybody hear me okay? I guess so. I can hear myself. So good morning. My name is Tam No. I work at Johnson Space Center. I think I know seeing half of you guys, familiar faces, but I'm going to introduce myself anyway. I work in the Software, Robotics, and Simulation Division. My branch, ER6 mail code, is called Spacecraft Software Engineering. Really, we are a software house, and better yet, we are a CFS software house. So this year's workshop, what I like to do is to share with you some of the CFS product highlights that we built at JSC. We built many products, and if you had attended last year or the year before, when was the last time? 2016 that you, Lori, that you described a very long list of products that we actually develop and maintain at JSC. So this one is only going to give you the highlights of the current products that we actually been maintaining, updating, and actually using in our current CFS project. And then I'll show you the list of those CFS projects at JSC that I know of that we, ER6, actually involved in. I'm sure I might miss out some, so, feel free to speak up. And then I would wrap it up with just what I consider upshots of doing software development with CFS. Okay? All right, so jumping into CFS product highlights. We at JSC had developed what we consider a generic command ingest and telemetry output CFS application. It can be easily expanded and customized. It supports multiple channels and multiple communication protocols, as well as the CCSDS space data link protocols. And it also works with the CF application to do CFDP file transfer. Now, for the telemetry output and the CI application, this has been developed, I would say about 2-3 years ago. And right now, I consider it in its maturation stage. We pretty much put it through the ringers. We use it in our CFS projects. It just recently got certified as a Class B safety critical flight software as part of the AA2 flight software project, or flight test project. For the AA2, with the telemetry output, we actually created 4 channels for downlink. 2 of them are actually Ethernet, and the other 2 are serial, RS-422. For the Ethernet, we have 1 channel doing raw data packets, and the other one is downlinking frame data packets. And then we have the other 2 serial channels downlink only frame data packets. And each of those channels can actually be configured to downlink at different rates. So that was very flexible. Another software CFS application that we just pretty much completed the development is called the time trigger scheduler. It's very much like the classical scheduler application that goes with CFS, but it uses the TTE network scheduling to schedule your message. So right now, it's not ready to make its debut yet, so you might hear more about it next year at the workshop. Oh, no problem. I thought there might be a question. Okay, so another CFS application, the software bus network. We developed this in collaboration with the Ames folks. It basically serves as a data bridge between CFS systems. Now, this app makes distributed network of multiple CFS systems across the network possible. And it also, just like CNTO, it supports multiple communication, UDP, TCP, serial for now. You know, you can always extend this to cover other protocol if you wanted to. So in conjunction with working the software bus network application, we developed a tool we call ProtoBetter. And what ProtoBetter does is that it would generate code to serialize and deserialize your CC-SDS messages for transmission over the network. The generated code is actually can be built into its own CFS library. We call it Protolib. It works with our CDD tool, basically to access the message definition in the database. But it can also run as a standalone if you give the message definition as a data input file. And right now, it's currently being used by the SBN application, but in the future, we want to make sure that CI and TO application is also going to be using the serializing and deserializing API as well.
Make mention of the endianess conversion part of that.
Yes, so serializing and deserializing actually has to do with two things. One is to pack your message so that you don't have to worry about structure or padding and all that. And the second thing is the by swapping. It will take care of both of those for you. Yes? So Protobuf, we started with that. Unfortunately, it doesn't work on VxWorks. So we decided, well, why don't we write one for ourselves that actually will work for VxWorks? Okay, so.
So does it generate the header files as well? Is that how it works on
the Protobuf, well, it's the CCDD tool that's generating the header files.
Okay, so it still is generating.
Yeah, Protobuf has its own parsing schema.
Right.
Yes.
I don't know if this was in your trade space when you were doing it, but have you done, or did you, when you're going with Protobuf, did you use, there's a version called Nano PB, that's the embedded version. That seems to work very well. Yep. In our process.
Okay.
We use the same thing for serialization and deserialization, all Protobuf.
Okay. Yeah, I am not aware of it, but that's good. Yeah, we'll check it out.
The standard Protobuf is a standard package with RTEM, so I don't know why it's hard to compile. So I mean, there are fielded applications using the stock Google Protobuf now. So I don't know.
Okay, I know our GNC folks are using Protobuf. It's just we just couldn't at the time. We didn't have anything that would run on VxWorks for us. Yes.
I have a question for GNC and the Protobuf or Protobuf tool, and I was wondering, for what reason did you go down the branch of designing something from scratch instead of using one of the buses that's available as like an open source system, like NanoMessage or something like that?
Okay, so chime in if you can, Lori. But here's how I understand it. Is that we did take a look at Protobuf. Yes, at first, because our GNC folks are using it, so we thought, well, why not? But then we found out that at the time that we needed to work on VxWorks, it didn't have anything. So then we needed something right away. So we started down writing this ProtoBetter code to extract the actual message definition from our own CCDD database. So it sort of worked well with some of our tools that we already have inside. And it's actually very lightweight compared to Protobuf as well.
One last follow-on.
Sure. That would be Dan Ray Prey, or you can contact me and I can get you to.
Actually, well, in regards to SDN, I didn't develop the original version of it, but any networking technology you want to integrate, you'll have to do some sort of bridging to those software buses or CFS. And that SDN code base is, 5,000, 10,000 lines of code. It's not a big piece of code. And so it would be pretty easy it'd be pretty easy to write your own app that would talk to your old bus, but SBN, the actual core of SBN is small enough that I think it makes more sense to write a module for SBN that would then talk to your network protocol. So we can talk offline about that.
Yeah, and I'd like to also point out is that just because we have the Proto-Beta tool to do the serialization, deserialization for us, doesn't mean you have to. I mean, SBN is already written in a way that you can plug in your own, deserialization if you needed to. Yes?
Just want to note, if people would try to remember to use the microphone so our remote presenters can hear, and if somebody does, if the presenter wouldn't mind repeating.
Yeah.
Just ask them if they run a mic around too, if that would help.
Yeah, sorry, I wanted to make a comment on that, I guess. I got my own. The Proto-Beta, why did we do that? As Tam said, we have this CFS Command and Data Dictionary that holds all the I/O for all the apps, and then that tool, in conjunction with this Proto-Beta, generates all these function calls that we're providing as a service that people can just use. So you can use it or not use it, but it worked really well. And then we took special considerations for real-time flight applications where a lot of the commercial packages that we saw, maybe we didn't look at them all, or have maybe more than you need, and maybe you have to go through the code, and certifying stuff like that is not always that easy. So we provided this, and it just kind of geared it towards small embedded systems, and took careful consideration with all the things we needed with bit fields and things like that. And then we went further to provide those calls to link it to SBN. So as end apps, and I think we did this with 20 or more nodes. The app, and we demonstrated it this past year, where we just hooked this to SBN, and then all the nodes, and they were heterogeneous. Some of them are big endians, some are little. Everybody's packing different, and it all just worked. So I think it was a successful thing that's available. Yes, again, you don't have to use it, but work well for small embedded.
Right, and the generated code is actually in C++, so it's easy to build a library out of it for CFS. Okay, so two tools, Command and Data Dictionary. Command and Data Dictionary has recently been very well received, and lots of interest from a lot of different group of people that's wanting to use this tool to define their system command and data definition. That tool the back end of that tool is a Postgres relational database, and it had a set of APIs that would allow users to write JavaScript that would extract data from the database. And right now we have JavaScript that can generate C header files, XTCE files even for the display folks, copy table for the HK application, and eventually I'd like to see this doing generating the scheduling table for the scheduler as well. And this has already been open source. You can actually get a copy of it from github.com. Our tool owner, Kevin, he updates this site quite often, so you can always get the latest from that site. Another one is a CFS 101 training that Dave had mentioned. It's basically a self-guided training package. It's really meant to target the software developers, not so much as going into the concepts of the framework or how CFS works and all that. Jonathan has a great PowerPoint package for that if you want to know about all the legacy and all that. But this one is really for the developer to see, like, well, how do I go about building the system from scratch? How do I add an app and create a new command, for example? It's just enough so that you get a feel for what needs to be done as a software developer. This is also open source. In the virtual machine, it's used as a tutorial workspace, so I've already downloaded all the latest version of CFE 07 PSP that is available on SourceForge, the open source version of those, and any necessary SenseOS library, system library that you might need. It's also available on github.com. Okay, so that's it for the product highlights. Is there any additional question for me regarding that? Yes.
Hi, I joined a little bit late. I was wondering if SBN and ProtoBetter
You
were
mentioned the
also on
ProtoBetter
GitHub?
tool. Is that available as open source yet, or no?
No, it has not. But anything we build, we do intend to have it open source if we can.
Okay, so are there plans to do that in the future, maybe?
Yes. I'm not sure how soon due to resource, really. Yeah. But is there a way for us to publicize or publish when things might be open source? Not really? Yeah. Yeah, email me. How's that?
Yeah. No, email's great, yeah.
Okay.
And also, you described this command and data dictionary tool, which I find interesting.
Uh-huh.
In order to be compatible with ground systems, the one ground system format it supports is ecstasy. Does it support any of the other native formats?
It doesn't, but the tool makes it very easy for you to write your own JavaScript that can extract the data from the database and format whatever kind of product you want it as the end product.
Okay, yeah. One of the difficulties we've had in the past is in working with the ground systems, we've still had to go with their native formats for a lot of missions.
Right.
Ecstasy is a standard, and some of the ground support systems are starting to support it well, but that's been a challenge.
Yeah, I mean, in the past we actually have JavaScript that will extract data from the database and spill out ITOS records, if you're familiar with the ITOS.
Yes.
Yeah, so we've done that. So it's very doable that you can, write a JavaScript to generate your own XTC or display files if you need it.
Yeah, I'll actually talk a little bit about that in my presentation. We do ITOS native generation and Cosmos, and we're looking at this as well.
That's great. Thanks.
Okay, so, all right, so like Dave, I also have my list of JSC CFS projects. So let's start with the Orion program. I know there's a lot of Orion guys here, so please speak up if I misspoke or you want to add anything. So the MPCV, it is a Class A safety critical flight software. One of their flight computer called the Vision Processing Unit is a CFS system. The more notable application on there would be the backup flight system that Lori will be talking about very soon. Their camera controller unit is also CFS system. It's actually an Ubuntu Linux running on an i5 Intel processor. And the notable app is the optical navigation application there. Okay. As I mentioned, the AA2, that's a separate flight test that's about to launch in May 2019. That is a Class B safety critical flight software. And it runs two computers. One is a redundant of the other. It is running on VxWorks OS on an SP0 Power PC. All right, so another one is called XEMU Flight Experiment. It's basically an advanced spacesuit. And what ER6 does is that we wrote the software for the caution and warning subsystem, and that is a CFS. It is a VxWorks also, running on VxWorks on a Leon 3 Spark processor. And then there's Seeker. Seeker is already manifested on the space station schedule to be launched in July of 2019. And that one is a Class C non-safety critical flight software. It's basically a free-flying robotic inspector that's going to be flying outside of the space station. I believe it's on a CubeSat form, and it's going to be basically disposable, which means we're not going to try to, get it back. And then the other thing that we're working on as well, this is a project to certify CFE on the VxWorks A-Ring 653. We've already done a Class A certification for CFE on the A-Ring 653, but it's Integrity OS, I believe. So this one, we're going to be working with the VxWorks A-Ring. Okay.
Sorry, quick question.
Yeah.
Oh, for the Class A, does that include any applications that are being Class A certified? Or is that all at the CFE and below?
It's just the CFE, just the CFE, OSAL, and maybe PSP.
Right.
Yeah.
Thanks.
Okay, so the last one, Aspect, is the newest project, CFS project that we have. It just started this fiscal year. It's going to be an ISS payload. But in the future, we can see this being used by the Gateway program as well. What it does is that basically it provides a common avionic and software platform for people to try out their application before they propose it to station or Gateway programs. Right now, we're going to target the Class C non-safety critical flight software cert. And it's going to be running on VxWorks on the SP0S processor, which is a later generation of the SP0. Okay, so the AES integrated testing project, this project has been running for several years now. It's basically is a place for multiple groups from different NASA sites to come together and run their autonomous system as a whole. So this is where SBN has been used extensively. Like Lori mentioned, we have sometimes up to like 20 CPUs in a network, and it's handling it quite well. So it was very successful. And then also, we also help the support the Next Step program, the people that actually interested in using CFS. We do provide tech support and whatever else that they need there for to basically use CFS. Okay, that's it for the list of projects. Any question for me before I go into the next one? All right, so let me wrap it up with what are the upshots of developing software with CFS. This list is basically a combination of my own experience with CFS and my observation after using it for so long. I mean, we started using CFS since 2010, starting with Morpheus Lander project. And ever since then, we are a big CFS user. So this is what I see as a big, big benefit for using a common framework like CFS. Is basically you increase your productivity. And the reason you can do that is because of the framework. The framework basically dictates the same look and feel for each of your apps. So it's very easy for you to recognize, to throw you a piece of code, and you can recognize, or you know where to go and look for things because of what? Of the code template. You know every app has a similar code template. It has at least a basic set of functions. It names the same way. You have convention all the way down to your file names, to your command MID, telemetry MID, your build file, your directory hierarchy. Everything is look very similar. So it's very easy to just pick up, from from an existing software and understand where you need to go and where you need to look for what you need to do. Because of that, you know, there's very minimal time to stand up an initial running CFS system before you even add any mission-specific capability. And I have done this for AA2. It took me 2 days to get all the apps that represent all the domains and the capability that we have to do for AA2 and get it up and running in 2 days. And all the apps will be actually running and it can be commanded, even though the initial command will be just no op and reset, but at least all the connections are there and your system is up and running, and you can see how you can add code to that system. I also found that because of the common framework, it's very easy for an experienced CFS developer to just jump into an existing project and pick up, because that person knows where to go. I mean, you know, if you have similar look and feel, I mean, people should not have any problem trying to nail down a bug, for example, of some piece of code that you've never seen before. But the fact that it is a CFS app, you would know where to go and look for these. And the nice thing is also you can actually train people ahead of time before you get them involved into your CFS project, because you can actually set up a training that show them the path and how to navigate through the code. This one is a good one too. The collaboration within the CFS user community really increased the level of software reuse that you can do in your system. And I want to say that open source software makes it possible. Without open source, I'm not so sure that we can get to the level that we are now. The nice thing about having a user community or a community of practice is that you can actually share your lessons learned or your best practices, the to-do and the what not to do, and therefore you can minimize your development risk. You also, because of that, can leverage the what you learn from current and past projects and apply that to your future project. There's a lot of CFS system configuration out there that you can actually take advantage of. You know, either it's been served before with that particular system configuration, or it has a PSP that's very close to the PSP that you need for your particular avionic board, for example. All of that can be reused a lot. Okay, so from the management perspective, well, why would our management buy into this? Well, first of all, CFS has its pedigree. So, you know, you can't, basically, you are using high-quality flight software, so there's no reason why manager would have anything negative to say about that. The other thing was that we now have better grip on our software development schedule and risk mitigation, because we are collecting, in ER6, we do collect software metrics and talk about comparing apple to apple. We are collecting software metrics on CFS projects, and you compare it to another CFS project, so that's a much better comparison than just a software project to a software project that uses a very different framework or design. And we see the increase in management support for projects that we propose that use a CFS, because, as I said, there's evidence. They saw the cost of schedule of the past and the current CFS project, and they saw the productivity and the benefit and the effectiveness of the framework. So as you can see, what I show you, the list of JSC CFS projects, those are not exhaustive lists. Those are fairly recent list of CFS projects that either just launched, just started, or in the progress of being completed.
I think
Yes.
I'm on. Okay, I'm on. One of the things that was presented to me, I think it either came from Jonathan or from the CFS team early on, is we did a model of what CFS or CFE might look like if you ran it through the Kokomo estimation system for effort on, and it was around $2 million of savings. And I'd like to publish that somewhere as another argument to management, which says,
Right.
if you use it, you can actually afford this project. If you don't use it, we're going to have to go somewhere else because you can't make the bills. And I think that's something that we need to get modeled in there, maybe get some more detail about how that model was developed so that you can make that argument toward management where it says, here's the numbers, and this is using a tool that they themselves would use to decide whether or not you could do the project. I think that'd be very helpful.
Yeah, I think so too. Yeah. Oops. Where is this? Oh yeah, I forgot to mention this one. Software reuse actually works, guys. I mean, it is a common framework. I mean, I don't know how many times I've got that story told to me about how we can do software reuse, but I remember spending so much effort into trying to make something work for my system as reuse. But this is real reuse. This is real reuse right here. And that's it for my presentation.
Thank you, Pam. Next, we have Laurie Prokop.
I'm waiting for hello. Oh, it's loud.
She'll be talking about
Hello? Hello, hello. Okay. It's loud. Oh, my God. Yeah, so, my presentation is on Orion's use on, CFS's use on Orion. And this is probably less about CFS and more about what these individual projects are. Because I think one of the cool things about CFS is that I could be a practitioner and you don't have to keep talking about what is CFS and how do you use it and how is this all going to work. The whole point of it is so that when you use it, you can use it and concentrate on the stuff at hand, like the apps that you have to write, the mission that you have to do, and you don't have to reinvent the wheel and rewrite telemetry and commands and the whole infrastructure. So I think a lot of the work that has been done in previous years, namely flight certifying it, human rating it, years past has enabled this work, I think. So I don't think it would have ever been accepted by a human program had we not done that effort. So I think the funding that NASA has put into CFS as an agency asset has really paid off here. So, here it is. So I'm just going to go on. I'm really going to talk about Orion program and these three specific CFS projects. I'm going to go through each one of them. So I don't know how familiar you are with Orion. This is the Orion vehicle. There is this is my pointer. This is the crew module for 4 crew members. This is the European service module, and then there's launch aboard system. I'll talk about we have CFS running here in the crew module and doing the flight experiment for the launch aboard system. I found this on Wikipedia, but I thought it was a good chart. So this shows the Orion program mission schedule. You can see pad abort 1 has already occurred. EFT1 has already occurred. I circled these 3 because we have CFS running on those 3 missions. Ascent abort test 2, That's actually upcoming. I believe they just shipped it this past weekend for launch. So that one's coming up. And then the next one after that is the EM1 mission, which is an uncrewed mission around the moon. I'll show that in a moment. And then EM2 is the first crewed mission around the moon and back. And I'll talk about each of those. But then the interesting thing is EM3 and beyond here are in gateway buildup, and I think I have a picture of the gateway. So we think that a lot of the work that we put on here for the CFS, at least these two, some of the projects when we talk about, they'll continue to live in these future EM3 and beyond missions for the gateway. So this is a picture of the EM1 mission. It's a long mission. It's 22 some days, 25.5 days. So it's almost a month. When I show you another picture later in the pitch, you'll see how it almost does a full moon cycle. But anyway, it launches and goes out to the moon and then hangs out there for a little while and then comes back. I'm not really going to go over all the sequences. This was available online that I found and I thought might be interesting. Yeah, there's going to be a bunch of CubeSats deployed. As again, I said this one's uncrewed and it's 25.5 days. And then if you look at EM2, which is the mission after that, this is the one with the crew. It's a shorter mission. It's a 9-day mission. So it's really not going to keep hanging out and going around the moon. It's going to go around the moon and back. But I'll go through the CFS projects that are on that. Oh yeah. So I don't think I have the gateway picture, or I might have it. Okay. Anyway, these are I highlighted the 3 projects that are CFS projects on those missions. The first one is the Orion AA2 flight test. I think Tam mentioned it's an AI tech processor with VxWorks. And then for the Orion missions, exploration missions 1 and 2, there's 2 boxes, one called a VPU, Vision Processing Unit, and then there's a Camera Controller Unit. On the Vision Processing Unit, the main thing, that whole box is a CFS box. There's data recording and other things going on that box, but also that box is housing the backup flight software, which I'm the lead for EM2. But on EM1, the code is already getting buttoned up now for EM1, and that's running CFS for entry phase. What we're doing for EM2 when the crew is on is we're adding the backup for all the other flight phases, all the dynamic phases throughout the mission. So that's going to fly fairly soon for entry. And it's a Sparkly on 3 with VxWorks. The other thing that's on both the EM1 and EM2 missions are these camera controller units. So I'll show a picture a few slides from now, but there's a lot of cameras on the Orion vehicle. There's GoPros, there's still cameras, there's a pile of cameras. And this camera controller unit is a CFS box that is controlling all those cameras. In addition to all those cameras, there's a optical navigation software, which is what I'm going to talk about, that's running on that box, that uses one of those dedicated cameras. It's kind of interesting projects. So talking about the AA2 test, and drawing an analogy between what was there on Apollo. So Apollo had a abort test, and then they had an ascent abort test. And it's very similar here with Orion. Orion already had their pad abort test, and this AA2 flight test is the launch abort system. So I think that's about all I want to say about that. This is a picture of the test. I think I wasn't the project software lead for this. Dave Swartout was the lead for this, and he gave me these slides. But I remember him saying, they say it's a 3-minute flight. at the time, I think they thought it was a 4-minute flight, so they worked on it 4 years for 4 minutes, and that was kind of the joke, is a year a minute for this flight. But anyway, so the flight goes up, and then they initiate the abort, and what happens is they separate from the launch vehicle and then reorient the capsule to get it away, assuming there is some problem with the launch vehicle that you have to distance the crew from it. So this launch abort system reorients, distances it from the launch vehicle, ejects the crew module, so the crew module can safely land away from the launch vehicle. And so that's essentially the flight. And what they're doing is recording the data the whole time, and then the data recorders are jettisoned, and then they're going to retrieve the data to make sure everything performed like it was supposed to. Yeah, so it's this is kind of an old chart. It's a dual string system, 2 flight computers for redundancy, controlling pyros. This is the block diagram of the components, the major components. The flight software is running CFS. The sim software is using Trick. And that was all reused. Also using ITOS on the ground. And you can see the tool chain here. Also, there's this data recorder, which is a Raspberry Pi custom app. So this was the bubble chart for the AA2. There's 2 SIGIs. I think they were redundant. There's a data recorder. And then you have your analog and digital I/O for the pyros, communication to the launch abort system, and G and C functions. Okay, so any questions on AA2? Not that I'm the expert.
How were the G and C functions, how were they defined and brought to you?
Yeah, so the G and Z functions for this were actually the primary code for the Orion vehicle, auto-generated and wrapped in CFS wrappers.
I can talk.
Yeah. Okay.
Can you just go over quickly what the automated flight manager is? Can you go over just what the automated flight manager is? Thank you.
So I wasn't totally involved with this, but I would say that the automated flight manager most likely moded the system to and detected events to control or orchestrate the rest of them. If anyone here is on AA2 that can say that better, please. Yeah.
That's pretty much it. We'll go ahead and, go ahead. Yeah, that's pretty much it. The AFM is in charge of maintaining the timing and sending the signals to the GNC, at least as long as other applications as far as what modes to switch into for their navigation systems.
Okay, so I think next thing I was going to go over is the OpNav app. I was the software lead of this. So this was a GFE project, government furnished app, and I guess I'll just say the way this was done was the Orion prime contractor Lockheed was building this camera controller box and all the apps in it, and they chose to use CFS. Late in the game, they chose to do this optical nav GFE, which was an interesting situation because what you had was the prime contractor and the government adding software to the same box. But what I can say was using CFS really enabled that, because what we ended up doing is building an app and delivering the app to the prime contractor as an inline function. So that was a really, I think without CFS, the integration cost would have been too high for us to do that kind of a thing. But both for this OpNav and later when I talk BSS, I think having that framework was an enabler to allow a prime contractor and NASA combined project with low integration costs, because everybody knows what an app is and people know how to plug in apps. So I think that it was a real enabler to do this kind of work. So anyway, what this project is, it's really cool. It's the first time, to my knowledge, that there is a way to automatically, on the vehicle, do trajectory course corrections for completing a mission or going to a destination. So if you lose comm with the ground, you don't have to have course maneuver updates from the ground. You can let this onboard software provide navigation updates to the flight computer. So it really enables, I think, deep space, and you don't have such a high reliance on the ground. Anyway, what this does, it determines position and range of the spacecraft based on optical image recognition. It self-calibrates itself to a high accuracy. For Orion, it is serving as the Orion backup navigation sensor if there's a loss of comm. So right now, Orion, it requires nav updates from the ground. If the comm is lost, it poses a loss of crew or loss of mission scenario. So this provides autonomous nav updates, and it's Class A safety critical. For EM1, we take images every 30 seconds during passes. I'll show you what those look like. There's passes to calibrate the camera and passes to actually do the imaging, and the imaging is of the Earth or the Moon. So for EM1, what they're going to do is validate this outbound to the Moon and then turn it on for use, if it works correctly, inbound, so that if we lose comm inbound, it will take the vehicle home. Okay, so this is sort of a historic picture. How does this optical navigation work? It's sort of intuitive. If you take an image of the Moon and you do the radius and you get an arc, you can figure out what the centroid point is on there. And if you have orientation, then you have bearing and orientation to the planet that you're looking for. And it's also very sort of historic. On Apollo, they did the same thing, but they did it manually. There was actually a sextant, a space sextant used in Apollo to verify and validate the course correction maneuvers on the Apollo spacecraft. So this would be the same thing, except it'll be done by this camera, and then the crew can look and decide if they want to use those nav updates. And so this is a kind of a cartoon of optical navigation, assuming you launch and you're on your way to the Moon, and then you want to get back to Earth. There's these red optical navigation opportunities, and then leading up to these burns. So basically, you would take images and then use that correction to do a burn, and then do a burn and do a burn, and come home. And so on EM1, there's one camera dedicated to this on EM1, and it's located between the two star trackers right here, and it's located right underneath the crew module here, so OpNav cam. This is just sort of a block diagram. There's this camera controller, and it takes images from the camera and then sends the nav data to the main flight computer to go into the guidance filter. And we have data going back and forth from to the Mission Control Center during this mission, but again, it's because it's the first time it's flown, we're going to want to monitor it. If we didn't have the mission control, that's really what it's built for, is to sort of replace the mission control. So this is the CFS bubble chart. It's really just one app that we delivered, and the other apps, there's a camera controller app that takes images with a commercial Pixelink camera and stores the image on the file system. When an image is available on the file system, these apps notify this OpNav app there's time for another image. The OpNav app runs, it crunches on the image, gets nav data, and sends it back out to the main flight computer. So this is kind of a time-lapse visualization of when they're actually going to run this this app during the mission. So imagine the green is the Earth, and the moon is blue, and it's throughout the course of the mission, it's going like this. It's going around the Earth during those 25 days. So this is the outbound leg. This is when they're going to be doing optical navigation passes, looking either back at the Earth or towards the moon to come outbound, and this is when we're going to be certifying it. Then there's going to be a couple of opportunities out here as we're going around the moon, but then coming back, they'll be doing these optical navigation passes on the way in to target the Earth for reentry. So I just threw some images in because these are synthetic images that we had to generate to test this. Surprisingly, the testing of this was probably the hardest thing because we don't have images with accurate time and bearing data to test with from real images. So we had to create images with very high accuracy. So we verified with thousands of images, but I just threw, this is a moon image that we were using. Then we had images of the Earth and moon, and it can pick out which target you want if you want to target the Earth or moon, even if they're both in the frame, just based on the different curvature. And then, of course, there's all kinds of things when you're dealing with cameras, different exposures we had to test. And that's all I have. Does anyone have any questions on... I think I had a lot more, and this is kind of an old pitch, but that's okay. Any questions on this?
Yeah, I've got one. Can you go back to the slide with the bubble chart, as you called it? So I'm still relatively new-ish to CFS. I've been doing it a couple of years, but just kind of on the side. Can you give a little bit of overview? I've seen a ton of these charts, but I never really follow along exactly. Like the green box in the middle, we have a framework that says 32-bit, and there's 64-bit apps, and how do they interact? And so, can you just give a general overview of these charts?
Yeah. So, this is kind of the traditional architecture chart. You start over here where the CFS system is layers. The apps are on the top. Then the core flight CFD service layer is here, where you have these services, software bus, publish, subscribe, all the services you might need to do communication between apps, and services for time, executives, turn on apps, turn off apps, restart apps. Table services is how you configure apps, because these are supposed to be data-driven. So in general, what you want to do is build apps that you can read in tables to configure them, that you don't have to rewrite the apps with everything different. And then the blue ones are these common reusable apps. There's a lot more of them that exist, but these are the ones that we used on here. I think the point with these reusable apps is you can just use them, right? As, like, say, the scheduler, you just put your apps that you have into the scheduler, and then they execute, and you configure them with tables. So as a user, you pick which operating system you're running on. There's several of these layers. I think I had a chart in previous pitches. If you're running on VxWorks, you use a VxWorks one of these. If you run on Linux, you run a Linux one of these. And then depending on your hardware, you pick a PSP. So there's multiple of these that exist. There's multiple of these. And when you do a build, you pick which one of these and these you use. So you have on your platform, you use these. This is what we're calling the framework. These three below, I think, when David went. So this is the framework that I think the community is committed to maintaining that for everybody and on the multiple things. And then there's this whole other question about all these apps. The apps come in many flavors. Some are Class A, some are not, some have flown before, some are in experimental. So the apps are sort of where the user community can pick and choose. And it's also where we hope the users, this is where you, in the yellow, spend your time working is in the apps, right? So the rest of the framework you use. But you had a question on the 64-bit. So in this particular one, we are using a 32-bit CFS build, but we have 64-bit apps running outside of CFS land, and we talk between the two with sockets in this particular thing. I think there are other 64-bit where the whole framework runs 64-bit, but in this one we're not. We're running a traditional 32-bit Linux on this one. Did that help? Any other questions?
Yeah, I had a question. So you mentioned that you're using these Intel NUC computers running Linux. Are these actually on EM1?
Yep.
Just the off-the-shelf
Yep.
computers, and is that Class A?
This app is Class A.
Okay.
The platform is not.
Okay, I was wondering. You're saying, off-the-shelf desktop computer,
Yeah.
Ubuntu Linux, and I was just wondering if all of that was considered Class A.
Well, no, it's kind of a strange situation. So the platform itself is not considered Class A because it's not rad tolerant, it's not rad hard, and it's Linux is not necessarily deterministic. The performance on this is not really hypercritical. We're taking images every 30 seconds, and then it takes a couple seconds to get the answer. As long as the data that comes out of this is within seconds, it's fine. So I guess, long story short, the solution, this software was written for Class A. The solution that you get out of this software, we have a lot of checks on, and all the way down from that computer all the way down to the main flight computer to make sure it wasn't corrupted. And then we have checks on the nav filter to make sure it's right. So we're sort of certifying the data to make sure that when it comes out of this, it's right. And we have all these safeguards in there to reboot if the processor crashes or something like that. So this app used to be on a more rad hard processor, but that's just where it shows up for EM1. In EM2, when the crew is on board, I'm not sure, they may move this over to a VxWorks processor that's on a different network. So it's a kind of a weird mix. The app is Class A, but the platform it's on is not.
Okay.
Okay, the last thing. So the third project that I was going to talk about is the Orion backup flight software. And many of you are aware, we're flying humans on EM2, and the backup is going to be on EM1 too. But for human-rated systems, they have to be highly redundant, and one of the main pieces of redundancy is a backup. So the main reason you build a backup flight software is to mitigate the risk of software common cause failure. So there's a standard safety there's a safety standard that says there could be, if there is a common cause, that's a one failure possibility where there's a common cause failure in the primary. It could bring the whole primary system down. So you fly a backup flight system. So in this case, we're building a backup flight system, and then and so that you try to mitigate the risk of this software common cause failure, you build in dissimilarity. So for EM1, we have a BFS for entry. For EM2, we're going to do it for all the flight phases. This is a joint. This project just started. It's 2 months old. It's a joint NASA Lockheed team. We're doing a mix of C and C++ apps within CFS on a Leon 3 and VxWorks. But as I said, it does all the dynamic events, ascent, entry, burn targeting. It maintains control of the life support systems, the power, and the comm. It looks out for critical environmental hazards, fire detection, prop overpressure, cabin depress, things like that. And also, a kind of a cool thing is allows the pilot to take the stick. So it has manual piloting capabilities for the vehicle. I threw this in, but just to show that when you build a BFS, this is like the BFS tool chain, and this is the primary tool chain. Some of the key things, we're on different operating systems, we're on different platforms, we're using CFS here. The BFS is hand-coded. And we are using the CFS Command and Data Dictionary tool on this. I know some folks had a question, can you use it for this or that? So we're going to build a whole bunch of new products out of this tool to integrate in with the Orion program, which has interesting formats for a lot of their data definition systems. And I'm not going to go over that anymore. This is oh, go ahead.
Be a fair comparison for a number of reasons, but on your primary versus your backup, it would be interesting to sort of do a comparison of the development processes and costs and quality, however you can come up with to measure that. It seemed like it'd be an interesting exercise.
Yeah.
Because they are so different in every way.
Yeah.
I don't know if anything like that is planned or.
Well, yeah, it is. So anytime you do this effort, we have to track and monitor our productivity, our resources that we're expending. So yeah, both the prime contractor for the primary system as well as our backup are definitely tracking our productivity and you know, probably in a couple of years we'll have the comparison. Yeah. This is just kind of a dumbed down view of the avionics, but the Orion system, oops, sorry. There's two, what they call vehicle management computers, each with 2 flight control modules. And then, so there's really 4 flight computers here in the primary system. And they're doing Integrity 653 operating system on Power PCs. And there's display units to the crew, and these are these camera controllers and the audio. But so the backup is on the same network, and the thought is if these all go down, you know, this is the one that takes over. And this is just the bubble chart, and this is already out of date, and lots of bubbles have changed, and some have gone away, and others have popped up. So. But anyway, we have prop and solar arrays and power, and there's a manual piloting app, and Eclipse, and this is our executive that's going to orchestrate. They are running the limit checker and the SC for EM1, and we're going to do that again in EM2. I think we're going to redo a different limit checker, but we'll be using the same SC. And we have a whole bunch of GNC apps that do burns on the different engines, and an entry app, and I think now we have another Ascent app that just kind of gives you an idea where we are. It's very notional at this point because we haven't gotten to even design phase yet. This is more for requirements generation at this point. Any questions? I hope I'm not over my time.
Thank you.
Oh, I think so. Thanks.
You mentioned for the backup flight software, you mentioned the Leon 3. It's just a single string? If you get it to the backup, at that point, there's no redundancy?
Yeah. Once you're on the backup, there's no more FDIR or anything because you're already in a 2-fault or multiple fault situation. So yeah, there's only one of them.
Okay, and there was another chart you presented which showed the backup and it showed the primary flight software. There were differences in every column, and I think the intention was for there not to be any common components. Is that one of the things that you strive to do?
Yeah, we did. I mean, that's the whole point, because the whole reason it exists is to eliminate or try to reduce the risk of common cause. So you try to use different everything if you can. Yeah.
Thank you.
Thanks.
Thank you.
Done, Laura?
Okay. I'll talk next to Chris.
Yeah.
It's Chris Knight
Talk
from
to mine.
Ames.
Yeah, why not?
And he'll be talking about the projects going on over at Ames.
Well, some of the projects.
Some of the projects, right.
I know that there's some small sat activity as well that I'm not talking about. I'm actually talking more about the projects that I work on, which is under the ASO element of the AES program. I forget what AES stands for. Maybe Lori or Tam remember what AES stands for. Yes, Advanced Exploration Systems. I always forget the acronym. But ASO is actually led by Jeremy Frank, who sends his regards. And I'm kind of more a systems engineer person who is also now the Ames Core Flight Software Change Control Board representative. So I'm on the regular telecons and I'm a proponent of CFS. But I'm just going to give you a little more what we're looking at. So let me back up actually before I get into more slide text. Is autonomy in our project is both autonomy in the computer science concept of your automated command and control of systems and diagnostics, but it's also our other hat is on crew autonomy, because of course you're going to Mars, you've got the hour speed of light delays. You can't have people on the ground commanding your systems or telling you what to do. You've got to be autonomous as an astronaut. So that's partly where we're heading as a project. So that's kind of getting into the Lunar Outpost Gateway, which we've talked briefly about. Is a project, a mission to put an orbiter on the moon that the crew can visit on transit to asteroids or to Mars, wherever they're longer duration missions, where they can kind of regroup, resupply, and then move on. But the gateway will be dormant 10 to 11 months out of the year, and that means there's a lot of maintenance on that system. Of course, it's around the moon, so it's not got the speed of light delay problems of going to Mars, but part of this is demonstrating autonomous operation of a vehicle. So here's some of the automation that AES program. There's the expansion. Looking at power management, avionics software, then just habitat automation in general. I'll skip forward, but so here's kind of, this is a demonstration system that we worked with the last couple of years in the IPAS, where you have a number of different power management systems or power generation systems that feed into power management systems that then feed into power distribution units that feed into different payloads. And so some of the software we've written is to automate the management of these power distribution units, and as you go into eclipse or your battery's running low, you need to power on, power off different devices, and there's different dependencies on them. So we've done some automation of that. Again, with the IPAS folks, the JSC, last 2 years, we've demonstrated our autonomy software in a flight-like environment. These SP0 PowerPC, right? The SP0 boards that are running in triplicate with a TT switch framework that drives a real-time environment. And so we've demonstrated that our autonomy, our diagnostic engines, and our automation engines can live in that hard real-time environment. So again, this is interfacing with the AMP system up here in the, let's see what's the button for the light here. The AMP system up here is an actual power management system demonstration unit that they have at JSC. Is it still at JSC? I think it's still at JSC, but Glenn developed, and it's feeding into our core flight software network of computers. All these are talking SPN from Linux systems into the VxWorks triplicate flight computers and back. And this is another VxWorks, but not triplicate. So that's kind of the work we've been working on, demonstrating that integration, and we can hope to continue that. And actually, nope, there's the animation. Oh, he's gone. It's like, Dave. So again, I kind of already talked to this. These aren't my slides. So again, some of the elements of our autonomy, we have a pretty, it's been in development for 10 years probably or more, a system of diagnostic elements that detect faults and try to diagnose root causes and then what the impacts of those faults are on your mission. And then of course, the next is to command elements to disable or shut down elements of the system. We also, our other hat, going back to the crew autonomy, is that we're not only scheduling of constrained elements on your vehicle, but scheduling and helping support scheduling of crew. So right now, if a crew member is operating your system and there's a fault that causes what would take 10 minutes to operate to take an hour, all of a sudden your crew member is having to reschedule their day or their week if they have to go back, the next day or 2 days later. So part of my other hat is we're doing demonstrations and experiments with ISS crew to look at not only diagnosing systems on station, but also providing crew interfaces so that they can evaluate what the impacts are to their day-to-day operations and where they need to reschedule, and giving them the autonomy to say, I want to approach this tomorrow and reschedule, so they can kind of start managing their own schedule. Because of course, again, if you're going to Mars and you're an hour time delay to ground, you're not going to be asking ground to manage your day. And then Plexel, and actually there's another system called Timeliner, which is more getting into automation of the systems on the spacecraft. I don't want to get into this chart. Kind of getting into some of the level of telemetry that we're analyzing, and then we don't worry about the actual text of it, but it's actually talking also about the CCDD and managing. I mean, you just get an idea, again, just looking at this eye chart, how much data, how many data elements we're dealing with. That's, I think, one of the interesting things is that the manned spaceflight program, the scale of the systems are so much larger than any of the unmanned systems we launch, that it's a good way to do scalability testing of core flight software and all the components that it incorporates. So this kind of gives you an idea of the number of data elements we're interfacing with, and then using the CCDD or CDD, I don't know if the acronym is these days, but CDD software to manage that large data dictionary. And then we also, because we're doing ground demonstrations, we've developed some tools to test with the AMP system that I talked about earlier. It's actual hardware that's spent millions of dollars building. We can't go in there and stick a screwdriver in an outlet and see what happens, right? They'd be fairly upset with us. So we've done systems to simulate faults and to replay telemetry. So if we want to run a fault and then do its analysis, then, oh, we want to do it again in the next 10 minutes and not have to go through a whole reboot. And then be able to command a simulated power system, so we're not turning off switches on the actual hardware. So here's kind of again, the diagnostic systems that we've developed, called ACOS, which is a whole suite of elements that the previous slides talked to. And this is actually the real meat of this is actually mostly in the title, which is that we've taken the EFT1, which is the Orion flight launch demonstration. We took the data sets of that launch, and we're feeding that through a replay system so that we can do analysis of that data in real time and at the same rate that the actual data is being generated or was generated during the launch. It kind of gives you an idea that the scale of things, that there's over 5,000 different failure modes on almost 3,000 components, and so we're able to process those failure modes and analyze them in a real-time environment. So this is kind of the high level what our projects have been working on in the recent years and what we're hoping to do in the next couple of years. So talk to me if you want to know more about this. But so 2 years ago, we spent a lot of effort on developing SVN into a more modular, capable, with the JSC folks, capable and kind of optimized environment for bridging multiple computers together in a spacecraft, and then working towards the VxWorks real-time environment, and then supporting the triplicate computer environment by adding a simple voting system, which right now is we're looking at redoing that. Last year, we integrated and tested out the CCDD or CDD system with JSC again, and helped support the ProtoBetter plugins for SVN, and demonstrating that with our diagnostic engine, the ACOS system. But next year, we definitely want to get back to talking to folks about EDS integration, because as you saw, the number of data elements, it's managing the data types is a real challenge as we get further into spaceflight ops. So, and then further real time, as we discussed earlier, the aspect demonstration, where we can do demonstrations of real time operations on a device on station would be great. And then further voting enhancements I mentioned previously. And then really, I think what we want to get into is autonomous commanding within CFS, and then autonomous commanding of CFS, because as we get flight demonstration systems in the spacecraft where you may want to change out, okay, we're going to do an experiment with these 5 apps and with these tables and configurations, and then, okay, next 10-minute slice, we want to do a totally different demonstration with different apps. Doing the management of CFS itself it becomes an automation problem that you have to bring up these 5 apps in a certain order and with a certain configuration, then you need to bring them down in an orderly fashion, bring up a different set. So I think that we're looking at maybe basically providing automation for CFS, and then I think the last bullet is that we're looking at, can we actually even put automation frameworks into CFS itself, so that limit checker and stored commands become more of a system scripting environment rather than a simple replay of commands, or there's LC has a RPN-like language, but it's really very limited, not fully functional. So anyways, that's all I have for my slides. Oh, back up. Sorry. Any questions? Questions? Thank you. We have a question back there. So I'll run back with my mic and hand it to him. Just come up to the mic if you would. Yeah, thanks.
Can you talk a little bit more about the voting that you're doing
So, yeah, let me back up to the kind of the architecture slide here. So, in this environment, this was 2 years ago when we did the demonstration of the voting. So we had the triplicate computers, and they're processing, doing diagnostics in triplicate in lockstep. And then what would happen is the data would then get flowed over SPN into the RIU computer here, which has what we call the level 1 voting. And we call it level 1 because TT has its own voting for its layer. So this is more an application layer voting architecture, right? Well, if you look at this, of course, you have this wonderful triplicate environment that then has a single point of failure, right? So what we want to look at next year is, can we do all the voting in this environment and do, again, even getting into automation. Okay, you have one of the three being voted out all the time. Something's wrong with that computer. Maybe it took a rat hit. Maybe we need to do a reboot. Maybe we need to take it offline. So that sort of more high-level, complex voting is, I think, the goal for next year. So, and we're actually looking at even doing a survey. It's obviously, we've been doing triplicate multiple, we've done it computers since before Apollo, right? So, doing more of a survey of what architectures can we support and what makes sense for the different models of different, manned spaceflight versus unmanned probes and all that sort of stuff. So,
cool. Thank you.
You're welcome.
Thanks, Chris. Next up, we have Alan Cudmore from Goddard. He's going to talk about platform technology updates. This should be interesting.
Okay, let's see. It sounds like my mic's on. Okay, I'm Alan Cudmore. As Dave has mentioned before, I was involved in the original development of the CFE core, which led to the CFS framework. And I'm here to talk about the state of the CFS platforms, at least from a Goddard perspective. And I guess for much of this work, Goddard's been kind of behind the curve when it comes to maintaining and updating the CFS platforms. We've kind of been just a bare minimum crew working on this. Meanwhile, all kinds of other work is being done everywhere else, and there's all kinds of new platform support being developed. So what we're trying to do, thanks to some of Dave's and the rest of the team's organization, is we're trying to get back into the management of at least the core platforms and a way of kind of making it easier to develop new platforms and plugging them into our whole framework. So I guess first I'm going to give you the state where things are and talk about some of the near-term updates we have planned, and then go into medium, long-term, and then just discuss a few things that are kind of not on the schedule yet. So anyway, when we talk about a CFS platform, we're referring to the operating system abstraction layer, the platform support package, which we've already mentioned a couple of times in earlier presentations, and then a lot of the underlying infrastructure like operating systems, board support packages, device drivers, file systems, even gets into development tools. So it's basically everything underneath the CFE core that's required to support a whole flight software system. And so in some general guidelines for a CFS project or mission, the OSAL should be pretty much, you should be able to use it as is if your operating system is supported. I'm sure we'll come into times when we need to modify the OSAL for a project. But in general, you should be able to stick with the VxWorks or RTEMS or Linux OSAL. For a CFS project or mission, there's always going to be customization required for a platform support package, or even the development of a completely new platform support package. But the goal here, what we're trying to do with our next effort in the platform area, is we want to provide complete OSAL implementations and reference platform support packages to serve as starting points for everybody's projects. And so what we would like to do is develop the proper documentation, test suites, and ways of independently releasing and plugging in PSPs. So, like managing every PSP out there and testing and making sure it still works shouldn't really be Goddard's problem. So I don't really think we have the bandwidth to do that. But what we'd like to do is provide the framework and the documentation and test suites so that someone could properly develop a PSP and then have it know that it'll work with the latest version of the CFS and that other people can use it. So the currently supported platforms, this hasn't changed much. We still support the POSIX, Linux APIs, but there have been a lot of improvements made to that. I mean, that originally started out as just kind of a development and prototype platform in the early days of the OSAL and CFS. We never really intended it to become like a flight operating system supported OSAL layer. But now, as we know, we're now using it on EM1. So there have been a lot of improvements made to that code. RTEMs, we're currently sitting at 4.10, 4.11 support in the official open source repositories. But work is being done to upgrade that to 5.x. I guess it's going to be 5.1. And of course, we're up to VxWorks 6.9 in the VxWorks support. And as far as our reference platform support packages that we have now, we have the old ancient MCP 750 VxWorks 6.4 platform support. That was the original PSP that we developed because we developed our CFE core on that board. We still have those boards in our lab, but I don't think you can even buy those anymore. So we kind of bought a newer set of these Freescale PowerPC boards, and we have those running VxWorks 6.9. And I guess that's kind of intended to replace the MCP 750 platform. Then, of course, we have PC Linux, which the word PC is becoming less and less relevant these days because Linux itself provides such a nice, stable, portable platform that our PC Linux PSP, with just some build changes, like some build rule, compiler rule changes, will run on any number of different platforms. We have it running on a bunch of different ARM Linux platforms. There's embedded x86. And, now we're even working on 64-bit ARM as well. And then, of course, still in the repositories is one of the Leon 3 development boards that we originally ported for our VxWorks development efforts. And then, of course, what Joe Hickey did was he provided the PC RTEMS platform support package. We used to have an older Coldfire-based platform support package for RTEMS, but we removed that because it really wasn't usable by anybody. It was just kind of a reference. So the PC RTEMS is at least more usable, where it'll build RTEMS for the 386 or 686 architecture and run on the QEMU emulator. And I guess what I'd like to talk about a little later is kind of consolidating some of these platforms to make them more like generic reference platforms. Just a little bit of what we're doing at Goddard in terms of CFS platforms. A lot of our work is, we're starting a number of CubeSat efforts. We have our Dillinger CubeSat, which has been on orbit for a little over a year now. And actually, we've really taken advantage of some of the CFS features in that CubeSat. We had a number of hardware failures in flight, and we were able to upload new applications, and we actually had to use File Manager to kind of piece those applications together because we couldn't upload the whole application with our bandwidth and our pass length. So we actually had to, one of the apps we had to upload, we had to kind of chop it up into 8 different pieces, upload all the different pieces, and then use the File Manager concat command to actually piece all those back together into one app that we were able to use. We have another couple of CubeSats that are actually ready to launch. STF1, which was developed by IB&B. So that's been delivered, and that's using the same FreeRTOS port on the updated down-space nanomine processor. And in series is going to launch on the same light, and it's using the Shrek space processor with Linux and the Xilinx Sync board. We have a few upcoming CubeSats. We're going to continue to use the Shrek space processor, or it's now called the CubeSat space processor. So that's based on the Xilinx Sync dual-core ARM, and the first couple of CubeSats are going to use Linux for that. We have a satellite called GTOSat. I think it stands for Geo Transsynchronous Orbit Sat. And it's a CubeSat that's going to use a custom Leon 3 FT that we're working on, and it's using RTEMS. And then, of course, we have JEDI and NICER. NICER's on the space station. Thought I heard somebody mention that JEDI is going to launch tomorrow. We have PACE and OCI, and we have WFIRST. So PACE and OCI are using a custom board with a dual-core Leon 3 FT, and an RTG4 FPGA, and they're using VxWorks. WFIRST is using a custom board that uses a Leon 4. In fact, we have a couple of those boards, and they're going to be using RTEMS 5. Let's see, so some of the things that we're aiming for, again, we're not trying to accomplish everything. We're just going to try to take a couple of reasonable next steps and try to make this kind of more usable for everybody. So that some of the generic platform updates, we want to integrate the SMP support for all of our platforms. And those require updates to almost everything, but not very big. So these updates, the original SMP support was first developed in an IRAD with Goddard and APL. We had a joint IRAD where we worked on integrating SMP support for VxWorks on a Leon 3 platform. And so now, since we've had lack of available people to work on platform support at Goddard, the PACE team really needed the SMP support for their VxWorks Leon platform. So they decided to take that work and integrate it into the latest OSAL, PSP, and CFE core just for the PACE project. So now what we're in the process of doing is we're evaluating those changes, and we're developing an integration plan for the official SMP support for the CFS projects. And so we're not sure it's going to look exactly like what the evolution from the IRAD to the PACE project, but we're trying to make it kind of the best implementation of the multi-core work, kind of take the best and accept input from the rest of the community. And then we also have coming up soon is the next-gen OSAL. So the next-gen OSAL is a refactoring of the OSAL code. If you look in the OSAL ports, you'll see a lot of duplicate code where it's doing things like checking tables, locking things, unlocking things, and and it gets down to just a couple of operating system specific calls. And so there's a lot of duplicate code between all those ports. So Joe Hickey, he took all that code and he kind of layered it such that most of the common code has been factored into kind of a common code base. And the operating system specific calls are in the individual operating system ports now, making each one smaller and making the code much more consistent. And so we currently have that in the development branch on the Babelfish repositories, and that's targeted for our next OSAL release. And it's also worth mentioning that this OSAL Next Gen is completely compatible with the current OSAL. So it drops in source directories for the OSAL next-gen drop in next to the current OSAL, and it's API compatible, and all the unit tests pass and everything. And then, of course, we just also advanced a network stream API into the OSAL, into the development branch as well. As far as operating system updates, RTEMS is probably one of the bigger ones right now. We're updating everything to work with RTEMS 5.x. We want to support SMP. We have support for the new dynamic loader going in. And we want to consider switching to the self-contained mutexes that are now in RTEMS 5 for performance. Supposedly those are a lot faster than the regular classic API mutexes. For VxWorks, we don't really have much on the plans except for supporting SMP and Linux as well. We want to be able to support SMP, and we're also looking at integrating ZenMI support, which I'm not sure if we should consider that the same as our POSIX API, but we do want to be able to support ZenMI as one of our platforms. And so overall, our goal is we want to have easy-to-use reference platforms for all three of these operating systems. And earlier I mentioned we have a couple of different RTEMS PSPs in our repositories. I think RTEMS is starting to look more like POSIX, where it can be pretty generic. So the goal is to have kind of a generic RTEMS platform support package, a generic POSIX platform support package, and if possible, a generic enough VxWorks platform support package. And the idea is that if you have a board running one of these operating systems, you should be able to start with our generic reference platform and make it work pretty quickly. Linux, we can easily get up and running in just a few minutes, especially with these nice distributions like the CFS 101 or even just the NASA CFE repository on GitHub. There's just a few lines of instructions to check out everything and then build it and run it. We kind of want to make the same thing happen with with RTEMS and VxWorks if possible. So let's see a little more of the medium to long-term updates. We want to provide the API documentation for the platform support package, and more importantly, a porting guide. We're often asked what it takes to create a new platform for the CFS, and we really want to try to develop a porting guide to help people with that. We don't have a set schedule right now, but the goal is to at least make some progress on it in FY19. And also, it'd be very nice to have a platform support package integration test suite. So if you develop a PSP, it'd be nice if you have some tests to run on it so that you can have a reasonable idea that it's going to support the CFS. And then, a long goal of ours has been to upgrade our Goddard compatibility and test lab. Right now we just have the old ancient MCP 750s, the newer PowerPC boards. We might have a Leon in there, but we really would like to ramp up our ability to test these things. So again, we want to provide the tools that the users need to develop and test platform support packages for unique missions. So, I guess Goddard, we don't want to be like the keeper of every possible platform support package in the world, but if we architect this correctly, then we can provide the framework and the infrastructure for everybody to go out and create the PSPs they need. And the same applies for operating systems as well, especially with the new next-gen OSAL. It should be easy enough to create a new OSAL layer for a new operating system. Just some of the random things I decided to throw up for, on the radar. We have kind of preliminary FreeRTOS support. It's been flying for over a year on our Dillinger CubeSat. And we haven't really had any major problems, actually no problems with the OSAL part of it. But none of our current plans at Goddard call for using FreeRTOS. I mean, I think we actually do have a couple of projects that may be using it, but our next round of CubeSats are going to be either using Linux or RTEMS. So we are interested if anybody wants to continue with FreeRTOS. FreeRTOS has a few challenges where it doesn't have the full operating system environment that VxWorks, RTEMS, and Linux do. You know, it doesn't have a dynamic loader. On Dillinger, we actually used a library we have called the Goddard Static Loader. And I've even heard of one user that has used like the NutX operating system ELF module loader and has been able to integrate it into FreeRTOS. Or, you know, we can just support single binary images without dynamic loading. On Dillinger, because our memory was so tight, we actually had a combination of that. Most of the apps were linked in with the base image, and then we were able to dynamically load the mission apps, which was critical to our success in being able to update that software. You know, another thing FreeRTOS is missing is a file system API. You know, and ideally there would be a nice virtual file system layer so that we could use POSIX-like calls over that. And then file systems is always kind of a grab bag. So when you say you support FreeRTOS, we have to come up with some sort of reference platform for FreeRTOS, hopefully open source, that everybody could use as a starting point for their work. Another thing we've been discussing recently is simplification of the operating system file system code. And we have that confusing volume table in there with the path mapping, and there's been some discussion about simplifying that and maybe just making it much more of a lightweight sort of POSIX file API over, instead of trying to manage all the volumes and mount volumes and format volumes and things like that. So hopefully we'll try to keep everybody updated with our discussion about that. And then of course, you know, we have a couple of other components at Goddard that we've used. The static loader that I mentioned, which was actually a lightweight ELF file loader that loads binary files into fixed locations in memory. We were able to use that in the place of a dynamic loader. We use that for our MMS mission. And of course, we have an EEPROM file system, which is a very lightweight file system that can really go into any type of memory. And it just has a very simple layout and API, and it can be used in kind of low resource conditions. I think because we have the EEPROM file system on GitHub, somebody even took that and ported it to work on an Arduino. Let's see. And so, of course, you know, I had talked earlier, probably last year's talk, about device abstraction ideas. We have a lot of different ideas, and projects are taking different approaches for device abstraction, but we really don't have an official direction yet for the CFS. And I really don't know if there has to be a single solution for device abstraction. You know, sometimes it's just very easy to, you know, have a device library, a CFS device library, and kind of avoid the whole PSP and operating system layer for your device abstraction, especially for mission-specific devices. But then also there's efforts on adding to the PSP API to include some sort of device interfaces that we could all use. So hopefully we'll have some more ideas and direction this fiscal year as well. And so I guess finally I have just some ideas about, you know, what would we like to see supported in the community? Do we want to have an ARINC 653 reference platform as one of our list of reference platforms? So we'd have VxWorks, POSIX, RTEMS. Do we want to have some sort of ARINC platform? Do we want to support some of these up-and-coming Internet of Things type of operating systems? Like Zephyr OS has had a lot of development recently. And NutX, to me, it's another one of these microcontroller operating systems, but it's much more feature-rich than something like FreeRTOS. And then, do we want to revisit CFS for resource-constrained environments, where we're talking about microcontroller class processors? So without trying to get us too far behind, that's what I have right now. Let me see here. Any questions? And anybody can feel free to, chat with me about platform-related topics, directions they'd like to see.
So you're talking about a network stream abstraction for the OSAL.
Mm-hmm.
And I'm curious, is there any platform you're targeting that doesn't use BSD sockets?
The one case I can think of is lightweight IP. Like if we're using the lightweight IP stack, they typically don't have the BSD socket API, the POSIX API.
Okay, yeah, I just figure every new API you add.
Oh, I know. It's the same with file systems as well. But again, we find, it seems to be the smaller systems don't always have the POSIX API. Yeah. Okay, and ERIC 653 as well.
Things like Xenami. I was looking for the microphone, I didn't see you earlier. But if you want to take advantage of benefits of like Xenami, that doesn't have the same API, and I know there's at least one other, but with the abstraction layer as it is, that's made it so that we have been able to do the ports over onto these platforms without having to make any changes into CFE or the applications themselves. So it worked out very well.
Anyone else?
Thanks, Alan.
Just a quick question. Real quick question. What's your time frame on the SMP sort of development?
Definitely this fiscal year. I guess I don't have an exact schedule, but the PACE project is moving forward with integrating the SMP APIs for their project, and we're starting to evaluate those APIs in the CFS community. And so, I think we're targeting the next major release. Dave still has the open source CFE 6.6 in the pipeline, which luckily is just not a technical issue.
Right.
And so we're targeting the next release after that, and hopefully, it won't be a year from now, but.
No, we shouldn't have to go through the open source process again, and 6.7, we went through, I guess I didn't go through that fully.
So, Alan, what are you guys looking at for SMP capabilities?
What are we looking at for SMP?
I mean, obviously, just being SMP safe is a first step, right? And are you looking at affinity or
we are
partition
looking
scheduling?
At affinity and obviously SMP safe. We haven't explored any of the kind of advanced features in RTEMS 5, like the schedulers that you have, the clustered scheduling or anything like that. But mainly it's affinity and our ability to manage the CPUs that we're running everything on.
You're going to focus on maybe pinning to one, since that's the only thing in ARINC 2015, and that also helps you avoid forced migrations. Because if you only can pin to one, then you can't get overlapping CPU sets. So I mean, it's terrible, but designing for the minimum sets kind of what gets you stuck to the stuff.
Mm-hmm. So. Yeah, and if you have any insight too, you're welcome.
We'll talk.
Love to hear.
I'm sure you will.
Follow-up, some of the other things we're looking at is just the whole power management thing in fault management. This core is faulted, so then we have to move stuff. So there's a bunch of APIs in that area as well, which are supported by the operating systems, but we need to expose them up to the fault management applications. Anyone else have a question? All right, good, thank you.
Okay, thank you, Alan.
Thanks.
And I was about to say, before I had the mic, 6.7, we can close that off. We have tickets assigned, and we're going through them. but we don't have a hard, I mean, we can take a look at an optimal time to get that closed off if the SMP work's done. So we don't, as far as I know, I don't think we have any other outstanding items that would really, right? So we will try to do the most optimal, and hopefully our legal, we won't have to go through the open source process again. So now Beth Timmons from Goddard, she's, so there was a little change of direction from last year, so that's when we brought in, really kind of pulled back our apps and any components at Goddard, and now she's the lead of that, and she'll tell you the status. Thanks.
Hey everyone, I'm Beth Timmons, and as Dave said, I am the product lead for the Goddard CFS products. Clicker. So today I'll talk about the current status of the Goddard products, some goals going forward, and then our release plans. But before that, a definition. So when I talk about Goddard products, I'm talking about apps, tools, and platforms that are developed at Goddard. That's a combination of open source products that I think many CFS users in the room are already familiar with, and then several other products that have not yet been released as open source and may remain internal. I'm not talking about the CFE, OCEL, or UT Assert library. Those are the framework, and that's managed separately. All right, so this is the current list of the open source products, and in this presentation I will be focusing on our open source products. So these are the 11 main apps that we have and their current release.
Sorry, please continue on that.
Okay, could you switch slides? Thanks. All right, so goals going forward for the Goddard products. A main one is to increase the communication and collaboration within Goddard, and hopefully through that also between Goddard and the outside world. We're going to try to maintain a more regular release schedule for the Goddard products so that those releases are more predictable. And then we also want to be identifying Goddard apps and tools that can be released as open source. So one of the efforts going on right now is to develop an app catalog for the Goddard products and then use that to identify what else we can release as open source. So there are 2 apps that we've already identified that I'll talk about later. And then we'll also be looking at releasing some Python-based table tools because I think table support is always a positive thing. So some key updates to how we're doing things on the Goddard side. A separate CCB for Goddard products, specifically apps, is going to be starting up in January of 2019. That's going to include Goddard membership to evaluate outstanding tickets. And we've already had a kickoff meeting to prioritize the current tickets. Right now, most of the tickets are ones that were already on the Babelfish server. One update that I should mention that's not on here is that we're going to be changing the CM process for the apps. So the ongoing development is not going to be going through the Babelfish server anymore. We've pulled that back, and we're going to be using the Goddard GitLab server and Jira issue tracking to make it work a little bit better with our development flow. The release mechanism is also going to be changing. So in the past, we've released the apps as open source through SourceForge, but we're going to be using the NASA GitHub group from now on. Each application is in its separate repository, so we'll be able to release them separately. And then the GitHub also includes an issue tracking tool, and that can be used to submit tickets on the open source apps. Another method of submitting tickets is through the CFS mailing list. So any problems or suggestions for the apps that go to that mailing list, I'll be recording in our issue tracking tool. So the overall release process is largely the same as what it has been in the past. So releases are going to be driven by hotfixes and mission and project needs. And like I said, we'll be trying to do those on a more regular, predictable sort of schedule. All releases do go through a formal test and verification process. So that includes unit tests, static code analysis, and functional testing. And then the release itself includes documentation such as test reports, user's guide, and version descriptions. So all the results of that formal testing will be released with the apps. So the new applications that I mentioned before are File Commander Extended and the Stored Commands Absolute apps. Both of these provide new ways to do onboard scripted commands. So the File Commander Extended application supports relative time sequences, with a binary file containing CCSDS commands. The file is read, and commands are put on the software bus. The stored commands absolute application allows up to 5 absolute time sequences to be run concurrently, and those sequences are specified using a text-based format. So 2 different alternatives there. Both apps are available to NASA. The open source release process has been initiated, but at this point it's kind of out of my hands, and I don't have a date for when those will be available. For the 11 apps that are already open source, this is the release plan for, nominal release plan for 2019. So the first order of business is going to be to try to release an updated version of each of these apps that is compatible with CFE 6.6. Right now, we don't know exactly when CFE 6.6 is going to be available as open source. So I'm going to try to time it as best as we can, looking at probably no earlier than March 2019 to get new releases of these apps out. And then after that point, the target is going to be rolling releases, trying to release a new app each month, resolving some of the open tickets on those apps. Most of the open tickets that we have right now are related to CMake and unit testing, so that'll be the bulk of the changes that'll be coming out in 2019. That's it for the main slides. Just a couple backups to point out. Here's a direct link to all of these open source applications on GitHub. And then the rest of the backup charts are a summary of the open tickets for each app and which ones we're going to be planning to include in the next releases of those respective apps. So I won't go through this, but it might be interesting reference. Any questions? Okay. Well, that's it for me.
Okay, next up we have Steve Lentine from Goddard. He'll be talking about the external code interface, which is actually a generalization of the Simulink interface layer, and he's got a lot of acronyms to talk about. And then he's also working with the CCDD tool as well.
Okay, howdy everyone. So like Dave mentioned, he asked me to get up and talk about some of the work that we've been doing at Goddard. So this is basically going to be kind of like 3 little lightning talks about each of these topics. Just a quick note about my background. I actually I work for Chesapeake Aerospace supporting Goddard Space Flight Center. I actually support Code 591 at Goddard, which is the GNC ACS branch. And so that's kind of my background. And then over the past couple of years, I've been getting more and more into the flight software regime and now some kind of flight software infrastructure type of stuff. So that's kind of where I'm coming from. So I'm going to start off talking about ECI, or the external code interface. So the idea behind ECI is that it's a framework, it's an app framework for integrating external code into a CFS environment. And so the idea here is you have some piece of code that you want to run in the CFS environment, but that doesn't have all of the CFS APIs and interfaces that you would need to do that. And so this code could be ephemeris models, it could be control algorithms, some code that you don't necessarily want to have to rewrite or modify in order to integrate it into your CFS system. And so obviously it's preferable to have to write as little code as you have to be able to do that. So for ECI, you provide an interface definition. That interface definition takes the form of a header file, and so you define several data structures in that header file to specify how you want ECI to talk to your code. You compile all 3 of those together with the ECI source code, and so that forms a CFS app. And so the ECI manages the communication between whatever your code is and the rest of the CFS system. And so that allows you to take advantage of all the other apps that are running in your CFS environment and all the other utilities that are available for that. So ECI is actually not new. It was formerly a part of the SIL. So I've talked about this a couple times in previous years, but the SIL, or the Simulink interface layer, really had 2 parts. There was a part that extended the Simulink code generation process to produce that extra interface header, and then there was the flight software portion, which actually integrated that code and set up all the CFS interfaces. And so all of this ECI project is we've split those two different parts of the SIL into two different projects. The SIL has a fair amount of heritage. It was at Goddard, that is. It was used on NICER for part of the pointing control system software. NICER is currently operating on the ISS. It was used on JEDI for their pointing control system software, and that's launching tomorrow at 1:30. It's in use by PACE in combination with the SIL for the development of their GNC flight software. And then WFIRST is also studying the use of ECI. And that's really where the motivation for splitting ECI from SIL came from. The projects that I mentioned earlier were all Simulink GNC development. And so this was a pipeline so that we could integrate that code easily into CFS. WFIRST is actually using 42 as their GNC analysis environment, which is a dynamic simulator. And so WFIRST is studying how they could take it or reuse that 42 analysis code as part of their flight system. And so we're looking at ECI as the method for integrating that. In addition to splitting it, though, we've also been working on updates to it. And so over the course of the past year, we've added support for critical data store, or CDS. And so the ECI interface now supports defining, initializing, and storing data blocks from your external code. And we added this because the PACE GNC has requirements that require using CDS functionality. We've also updated the ECI to take advantage of some SIL updates that we've made, which allows you to specify table validation functions through the ECI interface. And so ECI will take care of calling those validation functions on your parameter tables for you. And then we've also been kind of working on the artifacts that surround ECI. So we've created a set of requirements that describe the functionality of the ECI. We wrote and are continuing to implement unit tests to verify those requirements. And we've also been working on some documentation kind of explaining how the ECI operates, kind of training material. There are some limitations on when the ECI is useful. I'm not going to go through this whole thing, but the gist of it is that the ECI operates by grabbing pointers to various data structures and functions within the external code. And so basically those pointers need to be visible to the interface header in order for external code to work with ECI. And so the ECI open source release is actually hot off the presses. It got approved in the middle of November, and the repos actually just went up last Thursday. So you'll see the link up there in the slide. If you go there, there's actually not much there right now. I just haven't had enough time since last Thursday to get all of the code and documentation, everything up there. But that's one of my major goals for this week while I'm here, is to get that stuff up. And so yeah, I've got a list of everything that you'll eventually find at that repo. So we do have a series of UT-based or UT-assert-based unit tests to verify the requirements that we've written. There are example make files to get you up and running and compiling code with ECI. You'll find a bunch of documentation, including the requirements. We wrote a specification of the interface header that you have to provide with your code. And then we also have some technical overview slides just explaining ECI. And then I'm also working on putting together some examples. So I've got one that I'm just calling Simple App. It's designed to be a reference implementation of the interface header. And so that's just going to exercise all of the different, it's not necessarily a realistic code that you'd want to integrate into your system, but it does demonstrate all of the interfaces that ECI supports. And then I'm also hoping to put more examples up there. And this is kind of where the open source component of it is kind of exciting. If anybody out there has some code that they would like to integrate into a CFS system that you think would be compatible with this, please let me know, and we'll take a look at using that as one of the examples. So I'm going to move on to talking about the Simulink interface layer. And so the idea behind the Simulink interface layer is that it's an extension to the MathWorks Simulink Coder Toolbox that allows you to auto-generate the ECI interface definition that you need for your generated code to work with ECI. So you start off with your Simulink file there on the left. The Simulink Coder Toolbox will already, out of the box, generate C code that implements the algorithms that you've created in your models. And so our goal here is to integrate that code into CFS using the ECI. And so all that SIL does is extend that code generation process to produce the interface header that you need to integrate your code with ECI. And so the ECI and SIL really work together. The SIL generates the code, and then the ECI integrates those into the flight system. And so this kind of extension to the Simulink Coder Toolbox was developed in partnership with MathWorks' pilot support program. So I've gone over this in detail in prior years, so I'll just kind of skim through it. The idea behind the SIL is that it's designed to be an unobtrusive addition to a Simulink model. So analysts will often define debugging or analysis outputs in their models that you don't necessarily want to end up in your flight code. And so the way the SIL is set up is that the developers identify which pieces of their flight code they want to end up being generated into their flight app. And so the SIL provides several different wrapper objects that you use to wrap your Simulink parameters and your Simulink signals that are already in the model, just to flag those for the SIL that it needs to generate ECI interfaces with those. And then the SIL also provides a library of Simulink blocks that allows you to interact with CFS functionality. So there are blocks that allow you to send event messages. There are blocks that allow you to specify status flags. There are blocks that allow you to call table validation functions. So that gives you the ability to call into those interfaces from your code. And all of those wrappers and blocks and everything are designed to be no-ops in simulation so that they don't affect the analysis that the developers and the analysts are doing. And so SIL was also open sourced with ECI. I've got the link to the GitHub repo up there. You also won't find much up there yet, but again, I'll be getting that up throughout the course of this week. And we've also been continuing to update SIL throughout the course of the past year. So like I mentioned with ECI, the SIL now supports the auto-generation of table validation functions, so you can write your table validation function in MATLAB, and that'll go through the code generation process and be hooked up to your parameter tables through the ECI. And then we also now have a test suite to verify the format and the contents of the generated interface header. This is something that MathWorks had developed internally and was kind enough to release to us with the addition. Also, they released the actual SIL source code to us for open sourcing. So that's all going to be included in this repo. And then coming up, we're also looking at adding CDS support. Like I said, PACE has a requirement to use CDS, or Critical Data Store, for their GNC software. We've added the ECI interfaces for that, and so we're kind of working our way up the stack back into SIL in the near future. And then we're also going to be working on some documentation of the coverage that the test suite that we have right now provides, and looking to fill in any holes that we identify. And so kind of in the past, SIL kind of always supported ECI because they were really one project. And so I just wanted to add in that the plan is that the SIL will continue to always support the ECI interface, even though they're kind of being managed separately. And so now I'm going to move on to talking about CCDD, or the CFS Command and Data Dictionary. This is the same tool that a couple other people have mentioned. It's a Johnson-maintained tool. It's open source, and so I'm just going to be talking about how we're using it on the projects that I'm working on. So again, there's a link to the CCDD repo. CCDD is really a tool for managing software interfaces, and so I've thrown up the diagram that they include in their user's guide that kind of explains the architecture of CCDD. So in the middle here, you have a spreadsheet-like GUI that allows you to edit your interface definitions. There's a database backend. Up on the top arm here, they provide a scripting API that supports a number of languages, and the idea there is that you can implement scripts to generate whatever artifacts that you need from your interface definitions. And so they provide a number of ones, including C headers, ITOS record and display files, copy table headers, and several others. But we've also done some work to write scripts that generate the products that we're looking for. And then on the bottom here, they have a web interface, and then they also support a number of import-export formats. And so at Goddard, the projects I'm working on with CCDD is we're using it for the PACE GNC flight software development effort, and then we're also studying it, whether it makes sense to use for the W1 GNC flight software development effort. And so here, just going over the PACE CCDD workflow. So I've kind of taken that chart on the last slide and customized it for how we're using it for PACE. So we've still got the kind of the core of CCDD in here. PACE is using Git as our CM system, and so that's a distributed configuration management software. And so we've set up our CCDD workflow to kind of match that. So the idea is that whenever a developer commits their code, we've set up Git hooks, which are basically just callbacks that run at various points in the Git CM process. And so when they type git commit, it automatically exports the database from CCDD into a JSON file and then adds that to their commit. And so then that JSON description of the database gets pulled up into Git with the source code that it describes. And then whenever a developer runs git checkout, we have a hook that will take that JSON file and re-import it into CCDD. The idea being that whenever a developer is looking at code, CCDD automatically has the interface definition for whatever code they're working on. And then we're using this scripting API to generate a bunch of products for our development workflow. So we opted to write Python scripts. That's one of the supported languages by the CCDD scripting interface. We're using CCDD with our Simulink-based development. And so one of the main products that we get out of this scripting interface is a bunch of MATLAB scripts that define all of the data structures, all of the buses, all of the enumerations, everything that we need to do our development in Simulink in a way that's compatible with the interfaces that we've defined. And so we've written a CCDD script that spits out a bunch of MATLAB scripts whenever our developers are starting their development in Simulink. They run those scripts, their workspace is populated with all the definitions they need. We're also using CCDD to auto-generate ITOS rec and ITOS pages. So ITOS is a Goddard ground system. Rec files are basically the definition of the packets and tables. Pages define the format of the displays. CCDD does come with the capability to generate these. We kind of had to fork their scripts to be consistent with some of the PACE ITOS database requirements and data types that they wanted us to use. But the scripts they included were very helpful as a template for creating those products. And then we're also auto-generating an ICD. So we wrote a LaTeX script, a CCDD script to generate a LaTeX ICD. And so we compile that and get a PDF that describes all of our app interfaces. The way we structured that script is that the LaTeX it produces is modular, and so we also use some of those table and packet definitions in our algorithm description document, which is handwritten, but we're taking advantage of the automatic production of those tables. And then it's not strictly CCDD related, but I also just wanted to point out that we're also auto-generating a version description document to go along with our builds. So we use the GitLab API to get all of the commit messages that developers have entered, all of the issues that have been opened, all the issues that have been closed since the last build, and format those into a document. And so we've been very successful in using CCDD to kind of generate all the artifacts that we need to describe the interfaces of our build as we deliver that to the flight software team. And then I also wanted to mention, so WFIRST is also looking into whether or not CCDD would benefit their workflow. As I mentioned, WFIRST is using a 42 as their analysis environment for their GNC software. And so we're looking at whether or not we'd be able to reuse some of that code and integrate it automatically into a CFS environment through the ECI and CCDD. And so we're kind of looking at a couple of different aspects of this right now. We're trying to figure out the scope of what we might want to manage in CCDD, whether it makes more sense to just manage the GNC flight software interfaces, or if it makes sense if the wider WFIRST flight software team wants to adopt it. We're looking at how we'd manage the data products, or the interface definitions and the products for multiple teams. If we have both our GNC and our flight software team using CCDD, how do we manage the scripts that each of those are going to want? How do we make sure their definitions stay in sync? Do we go with kind of the distributed workflow that PACE is using, or do we try to adopt a more centralized workflow? And then also trying to identify what products we'd be looking for WFIRST. So C headers would be useful for integrating other apps with the GNC code. Assist is another Goddard ground system, and so RDLs are kind of the equivalent of ITOS rec files. They define the packets, whether or not we want to generate pages, and then also looking into generating ICDs. I just wanted to throw in a quick thank you to, so Kevin McClooney is kind of one of the developers behind CCDD. Just wanted to thank him for, he's been super responsive to issue and feature requests that we've been making through his GitHub repo. When we picked it up, CCDD kind of seemed to be geared towards a more centralized development strategy where you had like a flight software integrator managing all the interfaces. And so it's been through his help that we've gotten the command line interfaces and the import-export formats to a point where we can do these round trips through Git with all of our interface information. I also wanted to point out that we are going to have a splinter meeting later this week. So tomorrow at 2 p.m., we're going to meet, I believe the room is S2102. And so we're going to meet, the goals of the splinter meeting are just trying to get an interest in the community, in ECI and SIL, get feedback from you guys on what SIL and ECI would need to be useful for all the projects that are going on. And then we also wanted to revisit the topic of kind of the SIL unification. So Goddard owns a version of the SIL, which is what we've open sourced here. We're aware, I think there are at least 2 other kind of forks of the SIL that have happened at various points through development that are owned by other NASA centers. And those, after they've been forked, have continued to evolve in parallel. And so if there's anybody from those centers that are familiar with that here, we're just kind of trying to get an idea of what requirements have driven the parallel evolution, get an idea is if our open source version supports those. If not, is it possible that it would support it in the future? And so please definitely stop by if you're interested in using the SIL or ECI. I also just wanted to mention, so through Goddard, we've also been kind of assisting and advising a commercial company on implementing the SIL and ECI for their system via a Space Act agreement. And so we've been kind of providing guidance on their GNC flight software architecture and assistance with implementing the SIL in their system. So if you're working on a project that might use that, definitely feel free to contact us, and we might be able to set up something to help you guys out. And so that's pretty much my talk. Again, there's a link to all of the repos that I've mentioned. All of the tools that I've been talking about in this presentation are open source. I'm not affiliated with CCDD, but I just put their link up there as well. But for the SIL and ECI, please definitely open issues if you find bugs or have feature requests. So, thanks.
I just had a general question on the CCDD. So I work on a project at JSC that's using CFS and CCDD, and I noticed with your workflow. I don't know if you can back up to your workflow slide real quick.
Yeah.
I noticed. So I had this problem, and I noticed you had the same problem, and so I wonder if any CCDD people are listening. Just had a comment that it seems like CCDD is the usage of it is kind of designed around kind of a CCDD being a server of sorts to host data, whereas it looks like, so what you've done is great. I like the webhooks or the Git hooks that you're doing and everything, so that you can actually store your generated database files. And it seems to me that a more logical workflow to do what you did kind of, if you were to do the generation of these files at build time or something like that, that would make it a lot easier on the people using the CCDD. So, does anyone think it would be possible to go towards something like that instead of the server kind of architecture? Because I had to submit my message files to a person who then entered them in the CCDD and then hit a button to generate some files for me and stuff. And it sounds like you had to get some command line kind of scripting things going with Git hooks to do what you needed to do, because you need to store your actual message definitions somewhere, right? You don't want to just put them in a database and then not source control them. So I'm just throwing it out there. I like what you did here, and I just wonder if the CCDD could be kind of modified to suit this type of workflow.
So I'll just talk a little bit more about this. So this workflow is up and running. This is how we're developing our software. The idea here is we kind of ran into that same problem where it was going to be difficult to get a server set up in the government IT environment. And we also didn't want to kind of add the overhead of having to have somebody whose job it was to integrate all of the changes that these developers were making as they were writing the code. And so this distributed workflow is what we came up with. The idea here is that every developer working on our software has an instance of CCDD installed locally on their machine. And we use Git to synchronize the definitions as these developers work on their branches of code. And so what I was mentioning before, all of the changes all of the features that have been requested in order to make this workflow possible, Kevin has implemented those. Those are publicly available. So I know this kind of workflow is possible. You just have to kind of write the Git hooks to automate the importing and the exporting of the JSON products if you want to make it a little bit more seamless for the developers.
Okay, question off a remote attender. Nigel Zine, can someone ask if the PACE and WFirst dev tools are open sourced?
I just want to make one more comment on that last. So again, I'm not affiliated with CCDD. If there are feature requests, I would say go onto their GitHub and open an issue and make the request. And my experience has been that they're very receptive to that. The tools we're using in general are open source. For example, the Git hooks that I wrote to automate the process of importing and exporting the CCDD database are not open source. I don't know. We'd have to look into whether or not we can open source those. As well as the Python scripts that we've written are also not open source. And so we'd have to look into whether or not we can open source those. But the general tools, the frameworks that we're using are all open source at this point.
I was just going to mention that we're giving a presentation, I think it's going to be tomorrow, and it's got a component that is like the CCDD, but it actually auto-generates everything from the code or from the binaries at build time, and it would work for what you're asking.
Cool. Yeah. I think one of the other advantages of CCDD is that we also put all of our descriptions of our data points and data types and units and all of that into the CCD database, and so that allows us to auto-generate like an ICD, which contains kind of a more comprehensive description than just the data types and the packet offsets for people who want to interface with our software. That's it.
Hello? It takes a second. Okay, here we go. Yes. So Robert Hirsch will have two presentations. Ronnie, we're good with just.
All right.
We good going straight through? Okay. So we'll have two presentations from Robert on his.
So yeah.
Sorry.
All right. So I'd like to introduce myself. I'm Robert Hirsch. I'm with Johnson Space Center, and I'll be talking to you about actually a couple of projects back to back that have been using the CCDD tool as part of their software development process. And I'm not sure we'll be able to do it or not. Got some technical issues we're running into with the demo here, but I'd like to give a demonstration of the CCDD tool itself, just so you can actually see it and how it's able to generate files and do things. So if we can get that overcome, we'll do that. If not, I'll just sort of show a couple screenshots and let you look at it from that standpoint. So the first one I'm going to start with is the AA2 project, and you've actually, it's kind of funny looking at the presentations here. I didn't know exactly what everybody else was going to be talking about. So a lot of the material that I have has already been talked about by some people, but I'll cover as best I can. So just a quick overview. Again, we've already heard people talk about what the AA2 flight is going to be. It's going to test the ascent abort system on the Orion spacecraft. And basically, this is work that has been not outsourced, subcontracted back to the NASA to do for as part of the Orion project. So as part of that, we chose to use Core Flight software as the system that we were going to use and develop all that software. And we're actually using some of the direct mainline Orion code that's been delivered, and then just putting some CFS wrappers around it to be able to reuse it, especially the nav code. So we're able to, it's very, flight-like, high-integrity system that we're trying to build, and we wanted to be able to define everything. And so that's where we turned to the CCDD. So I'll get to that in a little bit. But basically, the overall system, we've got two CPUs that are running on AA2, and they basically run exactly the same code. They're able to check things back and forth. So if one goes down or whatever, we're able to recover. And the launch abort system, they each talk to it over their own serial link. Again, so if one of them goes down, it's still able to control the vehicle. And we had to coordinate since the computers are able to see each other. And so originally we had the same message IDs being used on both systems. And so if they each try to send, message 87 to be, some guidance system, you're not able to differentiate between which one it was. This is, and I'll get to this maybe later. We're using the original version of CCSDS headers with the 6.6 release. They updated. Now there's a new extended headers that allow you to have some more flexibility in those bits. But when we were developing this, we didn't really have that as the system that we were using. So we're using CCSDS version 1 as our header. So we had to make sure we deconflicted all our message IDs, even though it's exactly the same message. And again, I'll talk about that with the CDD. You define what a message ID is going to be for each message you're putting in this. But we needed to have multiple messages for the same type of message, one for each computer, so they wouldn't conflict with each other. Again, I think you've seen these pictures before, but basically just give an overview of the AA2 mission and what we'll be doing with that. And then again, we use the CFS wrappers around some Simulink autocode from mainline MPCV code. So we've already heard this before. The CCDD is the CFS Command and Data Dictionary, and that's something that Goddard intended to be used by many projects, and I listed some of those on there. As you can see by all the talks we already heard today, it seems to be in pretty wide use, although this is the CFS morning workshop, so I guess it's kind of a biased sample set. We've got a lot of projects that are using that, and as going along with that, all these, any system that wants to do it, you're going to have to develop, in some shape or form, a command and data dictionary for your system. So any space vehicle, you're going to have a list of commands you can send to the vehicle and a list of all the telemetry that comes down. And whether you manage that in an Excel spreadsheet or a Word document or a PDF or whatever, somehow you're going to have to manage every bit of every message that goes up and what it means and what Indianness it is and everything you have to manage. And that's done. And the problem or an issue with that is if every flight project is doing their own thing, just like with CFS, you can do a lot of work that you don't need to do. People have already done this before. If you can leverage what other people have done and not reinvent the wheel every time, you'll make your own development a lot easier. And so that's what the CDD was sort of started as. It was a way to make that more generic and reusable on multiple projects, so you don't have to have so much custom stuff. I'm not the main developer of the CCDD tool. That's actually Kevin McClooney. He's dialed on and listening in, but he wasn't able to be here today. So If I get too far afield, he might be able to correct me, but this is basically the system that we're trying to use. It's written in Java, and so it's able to be run on many platforms. You can run it on Windows, Mac, Linux, so you're able to use maximum flexibility that way. And you can create and modify the information that you need to manage your CCDD. So again, you have to have all those messages that are there, but that's not necessarily, you don't necessarily want to train everyone, or not everyone's trained in how to define things. And so he made a very simple interface. It's very much like Excel. You've got columns and rows and it's sort of a spreadsheet looking view, and you just sort of put in a message. Okay, I want a variable name this. It's an integer, or it's a float. You just define everything, several columns, and that's all you have to do to define it. The CDD takes it from there. The actual format so the CDD is here in the center. The actual database uses PostgreSQL, which is just a open source database that you can use. It's the actual format where it's stored, but again, that's not a very user-friendly interface. And so the CDD sort of acts like as a graphical user interface that users can use to enter information into or see information that's currently inside the database. And once you have a database set up, then you're able to either export the data or import the data using the import and export side. And there's also a web server that you're able to use so that if you want to see the data just using a web browser, you can actually get in and get the information out that way as well. So you're able to use an iPad or your phone or whatever and be able to see the information and get data in and out that way using a JSON interface. And then the final way of interfacing, which is what we're going to spend most of the time about today, is the script access. And so this allows you to write your own script, and there's several supported languages, and each of those scripts is able to put the data, basically it has access to all this information here in the database, but it can output it in whatever format you want. So you can make a script that makes a C header file, or an ITOS record file, or a Cosmos record file, or whatever your format whatever you're interested in getting. You basically have to have, you can either, if it's common type and somebody's already done it, you can just copy their script, or if it's a new format or you want to use a slightly different format, then you can modify one of those scripts, and you're able to, in very short order, get a script up and running and able to output data for your database. So that's sort of the high-level view of what we're trying to do. Let's see. Yeah, so that's sort of the emphasis. Kevin or people here at JSC, don't want to get in the business of writing every possible script that any project could ever want to do, because that's a big task, and that's not something that you want to bite off. But if we give people the tools, any program or project that comes along can modify or reuse an existing script and be able to make their own vehicle and software products that they need. So whatever it is that you want to get, you're able to do that. Even some things that are even more complicated, your schedule or network tables, copy tables. So if you've got multiple applications that are running on multiple computers and they need to send data back and forth and using time-triggered Ethernet, you have to have some elaborate scheduling tables that allow you to move the data each way and get there. And so that's some things that can be pretty complicated to manage and version control and keep all that stuff going. So I don't work on it directly myself, but I've heard that's been a pretty big issue with the Orion system, trying to get things and coordinating that. And so if we're able to help offload some of that work for future programs, I think that'll be a very, very useful tool to allow future projects to use. This is just a screenshot of the CDD tool itself. So like I said, I'll try to see if I can get on and give you guys a demonstration of that. Okay. All right, so I'm not. So folks online, I don't think are going to be able to see this. I'm not even sure it's going to work in here. Yeah, so actually we're coming up on lunch, so I can, if folks are interested, I can show them on my laptop. But it's basically a Java program that you're able to run, again, on pretty much any computer. you're able to see a database and open and close things, but I apologize, it's not being able to do that right now. So the good news is that'll help get us back on schedule if I'm not giving a demo right here, so we'll get lunch on time. So some of the things that we, again, like I said, every project has the ability to make whatever scripts they want to generate whatever files they need. So for the AA2 program, we used the C headers. We generated all the C headers that we used to send messages. So all the software bus messages for all the different apps, we defined those, generated .h files, and that's what we used. So we were able to, guarantee that all the different apps were able to publish or read data using those interface definitions. We also defined all of the message IDs that were used. So we defined our custom apps, but we also defined the message IDs that were in use by the standard stock CFE apps so that we didn't have any conflicts, because if that app ID was already in use, we couldn't reuse it. So we didn't necessarily define all the messages that all the CFE core was publishing, but we have ways of reserving those and basically knowing that those are already being used and not to reuse those actual numbers. And the scheme, it was pretty simple. We only had 2 CPUs, so we basically just added a hex 100 to all the message IDs for CPU 2. So whatever CPU 1 sent, you just add a 1 to it, and then that was the, so if it was 87 on one, it was 187 on the other. So we just added hex 100 to each of the message IDs, and that's how we were able to track multiple messages being sent out on each of the CPUs. And that also, when the ground software would receive that data, it was able to tell if this was the CPU 1's version of this parameter or CPU 2's version of the parameter. And then the other big piece of information that we generated was the HK copy table, and this was pretty extensive. For the system where we output the data, we actually had 2 serial ports that were running, and that was that's what the flight interface has. To get data to the ground, that's all that was available. So we couldn't use Ethernet during the flight because the Ethernet cable is not that long. And so we can use that while we're on the ground, when we're on umbilicals, but once the vehicle takes off, the only way to get to the ground is through a serial wireless link. And so it's much more rate constrained. I mean, I think that link, it's under megabit per second as far as the throughput. And so the onboard telemetry is much, much greater than that. And so only a small fraction of the data could be selected for downlink. And so it's sort of a Frankenstein. We would go into individual messages and say, okay, this parameter I need, and this parameter I need, and this parameter I need from all these separate messages, and we would make one composite message. And that's sort of that's the whole point of the HK. That's kind of an ironic or a not intuitive name, housekeeping. I wouldn't normally think of that, but that's basically the housekeeping app. That's its job in life, is to slice up all the other messages that are on the bus and get just the critical information, and then it sends out a new message that's just a Frankenstein message. It's the important pieces and parts of other messages, and that's what gets downlinked to the ground. And so as you can imagine, creating, if any one of those input messages changes, moves things down or moves things up, add a parameter, that copy table needs to be completely regenerated because all your offsets will be wrong. And so the copy table is just basically a list of mem copies that it tells it, grab these 5 bytes from this message and put it in this other message, and grab these 10 bytes from this message and put this other message. And it's just a table of mem copies to copy all the memory and make that Frankenstein message. And so trying to do that by hand it really would be a fool's errand. I would not suggest that to anybody that you have any positive feelings towards. It's a very error-prone process. You make one typo and the entire system will not work properly. So trying to keep that managed and in order was critical to what we were doing. And so we were able to do that. And in addition to defining it as telemetry, since we had 2 serial streams, there was an A and a B that had different data going down it. Not only we had to say, okay, this is an important message, we had to say which of those other messages to put it in. So we had to manage multiple output streams. So not only is it telemetry, but which path of telemetry. So it got a little more complicated there. We used ITOS as our ground system. So we, again, generated the ITOS rec files that we used to define all those messages. And again, it had to know about all these different paths and all the different ways of coming through. And, obviously the stock one that, you would grab off GitHub would not have that capability. But we, were able to add the extensions that we needed to add that extra complexity that we had for our system. Let's see. And then in addition to running live, we also wanted to be able to decom the data afterwards. And so if you run a flight and you want to be able to grab all that information, you basically need the same data. You need to know what all those messages had inside them so that you can export the data in some kind of MATLAB file or something that engineers can look at to be able to analyze it. The format we used for that was just comma-separated values. So we would just put all the different parameters at all the different times. And we used some tools to generate those and also used some CDD outputs to be able to run those automated tools. So it was able to automatically look at the raw binary that was stored and extract all the CCSDS payloads out of or the parameters out of those messages. And if anybody has ever used ITOS, it has a similar thing, sequential prints to output CSV files. You can do that directly in ITOS, but the external tools that we had, were significantly faster, and we were able to get the data quicker to the engineers, which they always appreciate. So, and again, we didn't want to make different things or have them be custom. It's a custom tool, but we didn't want to handwrite those tables and everything. So as somebody makes a change in the CCDD to update the information, then you can turn the crank and get all these new header files and all the new rec files, but you also get the new decom files as well. So everything stays in sync, and you know that you're getting the right data at the right time, because everything's based off the CCDD. So that's sort of our authoritative source of where we store all the configuration information. And since all the products are generated from that keeps everything version controlled and in line with each other. Let's see. So again, the CDD was integral to what we were doing. We didn't wait until after the system was done and then create this as a documentation thing. This was something that we iterated on many times during the development process to get the information that we needed. We were able to track, in addition to doing the main line that we call the OI information that came from the flight computers, there was also some DFI, so the flight, some pressures and sensors and different things that are on the vehicle that weren't part of the main operating system that was running core flight software, but we wanted to be able to visualize those, and so we added that information into the CDD as well. And so we were able to see that the different temperatures and pressures and whatnot that were being monitored that weren't even part of core flight software, but we were able to integrate that and be able to display that in the same ITOS thing as well. So that allows additional insight for the ground controllers. They can see the DFI as well as the OI data at the same time. Again, all this quick look processing, we want to be able to process this data and be able to get it as quick as possible to the engineers to look at afterwards. And then the entire system that we did had some software verification work that we had to do. So basically we had to verify that parameters were being sent or commands would have the expected effect on the system. We were able to generate, again, this wasn't me doing the development, but people on the team were able to generate some automated scripts using, I think it was under Python, to be able to automate all this testing process. And so we were able to use the CDD generated files to help use that automated testing framework to verify that, yay, verily, the right parameter was showing up on the right pieces of each message and verify that our system was working as intended. So it helped with our software verification activities. And then additional work, this didn't actually really use the CDD as much, but it was trying to remotely control our power supplies. So you can't have somebody go up and flick off the power supply right next to the launch pad, because as they get close to launch, there's certain rings, 3 miles out or something, that you can't have people next to a vehicle when we're at KSC. And so we want to be able to remotely control our systems. And so we were able to interface with that as well. So future work, we're looking hopefully launching, I think May 1st is the current estimate for AA2. And we're actually working with the education outreach. Hopefully in the next month, we're going to be releasing a student competition, basically looking for junior high and high school students to build a graphics visualization, so sort of similar to this, just a CG thing where we pass them the position of the vehicle and they do some rendering thing as an app development. So it's sort of a computer science education plan. The winning team will be able to come down and view the test flight and see their app in use at KSC. So hopefully that'll help get some engagement with the students. And so, again, sort of a summary, we've been able to use the CCD tool quite extensively on the AA2 program to generate a lot of the tools and things that we need. And hopefully we'll be able to pass on the lessons learned so they can be leveraged in other programs who decide to use the same tool. All right, so I'll go ahead and stop here for questions on the first one.
Any questions?
So this is okay. Nigel Singh is asking, is the CCDD Cosmos and ITOS export scripts available?
I'm not positive. I have made a Cosmos export script. I'm not sure if that one's checked into GitHub, but I can work and get it out there if it's not.
Okay, so he just says asking for testbed software development for the DART mission, considering CCDD for C++ code and Cosmos generation.
Yeah, so that's actually, if I had my demonstration, I can show it to people. That was actually one of the things we ran into. Originally, CFS is largely a C-based application. And so the CDD tool originally was building C header files, but working with BFS program, we wanted to be able to export or create class headers. We want to make C++ header files. And so there's more information that's required if you're going to do a class because you have to do the inheritance and whether it's a public or private or protected. So there's a little more information that had to be there. And so we actually were able to go through and add extra information and be able to export. So we have a script now that can export C++, it's still a header .h file, but a class header file. So yes, you can. We do have that capability as well. So generating scripts for C++ is possible, although originally it was only C, but we have extended it to do C++ as well. And like I said, another program I was on, they wanted to use Cosmos, so I went through and Cosmos had to have everything completely flat. So the CDD tool I wasn't able to show you, but it's hierarchical, so you define structures that are components of other structures that are components of other structures all the way down, whereas Cosmos wanted everything completely flat. So you had to unroll everything before you can make a Cosmos file. So you're not able to take advantage of some of the hierarchical kind of stuff, the architectural layout of stuff. You can't define a quaternion and then reuse that throughout the thing. You have to just put the XYZ element item by item in your structure. So there were a couple things that had to be done with that, but it is very doable.
Okay, thank you. Any other questions for Robert?
All right.
Everybody got stamina for one?
Yeah.
One more? Okay.
I think everybody's getting ready for lunch in there. Thinking
didn't schedule breaks either, so.
All right. So this presentation is on the command and data dictionary, the use on the Habulous program. Tam already mentioned some of the AES work that we've done, and so this is part of that as well. Again, I'm still Robert Hirsch, and we'll be talking about the work we've been doing here using the CDD tool. So again, I'll talk a little bit about the Habulous project itself, and then maybe briefly say the CDD in case somebody's listening to a recorded version of this later, so they know what it is. But talk about some of the CDD products that we did for the Habulous project itself, and then other development work that we did on Habulous and some of the new things that we're hoping to do in the future. So Habulous is an Earth-based test bed, and so it's basically, so the picture there, that's a Hab module on the back, and so they've got computers, and this is sort of represent what a space-based Hab would be here on Earth, and so we're testing out some of the hardware and software components that might go in a future Hab, but it's not designed to be a flight program. It's not a flight project, but it's a development prototyping effort. It's represented by many organizations, NASA centers and other aerospace organizations. And because people were it's so distributed, and people were working in different time zones and different areas, it made it very critical that we manage the interfaces. Not only were people geographically separated, but different teams had made different choices on the architectures. So it wasn't a centralized thing where everybody had agreed on the architecture they were going to use. I mean, some people used Raspberry Pis. People were using Intel chipsets. We used Power PCs. I mean, we had many different architectures, different 64-bit versus 32-bit decisions that were being made independently at different centers. And so we had a massively heterogeneous computer architecture to deal with. And so anyone who's worked with that knows there can be all kinds of byte alignment and bit packing and all kinds of issues that are come up when you deal with different architectures. And so that was one of the major things we knew we were going to face with Habulous because of the way we were distributed. And we made pretty good use of the SBN, Software Bus Networking application. It's a CFS tool. And it basically lets all the different modules. So most spacecraft, current spacecraft only have one processor. So we don't have to worry about multiple CPUs communicating and moving data back and forth. So this is sort of new territory for CFS trying to work and coordinating massive number of nodes, and well, massive is relative, but a large number of nodes to be able to communicate and share data. So an app can be run on one computer, send the data to another computer, and have that app receive that just as if it had been published locally. So that's sort of the point of SBN, is to be able to abstract away the fact that two applications aren't running on the same CPU. But again, if those CPUs underlying didn't have the same native, Indianness or network or size of an int and all that kind of stuff was different, then it's going to be very challenging to move that. And so we used SBN to sort of work with that. And then some of the people that were working on there didn't even make the choice to use CFS. And so if we're trying to communicate with them and they're not using CFS, we sort of had to make a way to make them pretend that they were CFS. So we developed a library called SBN-lib that was just a package that you can include in a normal C program that would let you spoof or look like you were a CFS node to somebody else. And it would follow the SBN protocol and communicate with all the other CFS nodes, even though you weren't actually a real CFS instance, and you were still able to push data in and out using SBN-lib. So it's sort of a halfway to CFS for people who couldn't jump all the way there. Nobody has to worry about reading this. There won't be a test later, but this is just sort of giving you an idea of all the computers. So again, we've got the 3 flight computers that are over here running VxWorks and the time-triggered, multiple computers over here. So you can just look at all the numbers of systems that are distributed out. I think this has like 16 different computers that are running, all moving around, and there's different networks. So these computers are able to talk over this time-triggered network. There's a separate Ethernet switch over here that connects these. And we actually even had to worry about bridging back and forth. So data from here comes into here, gets so there were different networks that were, not everything was connected to everything else directly. So we had to worry about relaying the information to different systems. So it really was an ambitious effort and be able to get things working. And again, CDD still is the CFS Command and Data Dictionary. And we're using that. Let's see, I can skip most of this since we've already talked about it. Actually, this is all identical exactly to the last slide. Okay, so this is some of the stuff that we did for CFS on Habulous. So these are all the different messages, and then the message IDs. I had to blank out the name for export control reasons. They didn't think that would be appropriate to show everybody. But we had to manage and make sure there weren't any duplicates. And if I had the tool running, I could show you if I had put exactly the same number between these two, then these would get highlighted in yellow automatically to let you know that there's an issue and a conflict. But it's able to manage all the different message IDs. You can enter, change the numbers. In addition to defining it in the tool, you're also able to output the C header file or the .h file that has all the pound defines for all those numbers. So your program never has to worry about the actual number. It just uses ACOS DE impact request MID in all your code. And then this file, the .h file, you just include this .h file that defines all the message IDs in use on all these different CPUs and all the different in the system. So Habulous was using the CCSDS version 2, so we were able to leverage that and be able to, so that was a new effort that we were doing, be able to generate header files that took advantage of the new app ID, system ID, subsystem ID that is used to define all the different messages that are sent off on the software bus. And so that was something we had to add to our scripts to be able to manage that. Let's see, defining those messages. We generated XTCE files. That was what our display team used to generate the display pages for the ground interface system. And so we were able to export the data in the CCDD so that it would be able to be used by them. And then they had a drag and drop thing where they were able to take any parameter and build a page. They could probably give a whole presentation on their system called Chisel that they use. But our only interface with them was to output the XTCE, and they were able to manage it from there. So it made a nice interface for us. Generating proto-better code. We talked about this earlier. So these different computers that are on different systems, different Indiannesses or different architectures need to be able to communicate with each other. And so the proto-better code, again, this was just a script. We made a script, the proto-better script that would run on the CDD and generate these proto-better files that would automatically take care of the byte swapping and packing, serialization, deserialization of the messages so they could be sent and received with different computers. So all that code, the proto-better code is really a Python script that was written that just runs on the CDD tool. And so all that stuff, we wrote it once, and then we're able to generate as many proto-better files as we want to do. This is just sort of a, I don't know if anybody's looked at the new definition, the CCSDS application ID, but this is where it originally was, where you had your application ID. And so now there's app ID qualifiers that go into it that sort of tell you which one you are, and then the app ID, there's app ID qualifier and then subsystem. So system and subsystem, they'll go along with it. And so all these things go together to generate your message ID. And the programs are able to choose individually which one that they're wanting to do. And so, we chose to use this many bits, the application ID, and this many bits of the subsystem ID. And we didn't actually use any of this one because we didn't, everything was in the Habulous system, I guess. But we were able to generate it that way. So it gives more flexibility as far as, because we were going to run out of message IDs just because of the number of CPUs that we had, and we were making multiple copies. And so we did sort of need to take advantage of the CCSDS version 2 in order to have enough message IDs to go around all the different computers. Yeah, can you go to the next slide for me? Sorry? All right. So like I said, some significant work we did on updating the CCSDS version 2. And our XTC export allowed for drag and drop displays, so people can just go in and build their own display pages automatically. We're able to work with all these different computers. And even if you're not running CFS, you can use SBNlib that, again, uses all this same code to be able to allow external applications to talk to CFS applications. And again, just like with AA2, this was all done in line. So as we were doing the development process, we were updating the CDD and modifying it and making the changes as we went. So it's not a post-development activity to document what we did. This was something that was used extensively during the development process to help us get things where we needed to. And again, we ran into things mid-year on the message IDs and had to change our definition of things, but it was better to do it then than to wait till the end of or to find out later that we had that issue. So that was good. Some future work that we want to, so we've successfully been able to use it to generate a good percentage of the code on Habulous. And some of the future things we like to do is the time-triggered Ethernet tables. So generating all those configuration tables that go into the time-triggered Ethernet to coordinate message passing from different computers. And CFS schedule table, so be able to, for each, those 16 different computers, each of those has to have a unique schedule table on it. And so trying to manage each of those individually can get kind of cumbersome. So be able to have it track and manage all those schedule tables. And then automated CDD to SysML export, so people who want to use SysML be able to use that and get that information on the system. So with that, I think we're pretty close to being on schedule.
Any plans to
Yeah.
open source the SBN Live?
Yeah, so the question is if there's a thought to allow the SBN Live to be used by anyone. I think that would be very useful to do and to allow people to have access to that. There's actually a couple different people have sort of, just like there's different versions of this still. I mean, there's been a couple different methods. People have had that same idea and even called it the same thing. So yeah, I think having something like that that's out there and is available for people would be good. I don't know that we have a specific release date for that. Tam might be able to comment more on that, but I think it would be useful to be able to let people to use that. But several different teams, not just even at NASA, have been able to use that to communicate. So I think it is but they're all working contractors. But being able to open source, it's no different. It's just like the CDD. The CDD you can get off GitHub. There's nothing in it that's export control because you have to define the interface. We don't give them the database of the AA2 mission. We just give them the CDD tool and you can build whatever you want from it. So the same thing. There's nothing proprietary about the interface. I mean, you have to know the messages you're going to send before it would be useful. So as a tool, I think it should be very easy to be open sourced.
Okay, thank you. Thank you, Robert. I just want to say thanks to everybody that presented and for all the engagement. This was a really good CFS workshop. Actually, I'm looking for an ESOL. So if we want to have some splinters, then maybe you could have a demo as well. I think we might have some sign up. We're working on getting a sign up outside the door, so maybe people during certain lunch hours throughout the week you can have things like that.
Yeah, sure. Okay, thanks again. It was a great session this morning. We're going to kick off the main body of the workshop just after lunch. We do have lunch available outside at the table, so please help yourself to the lunch. I'm sorry?
Oh, is there an online question?
Oh, okay. There's an online question. Let me finish what I was going to say, and then we'll go back to the question, and then we'll break for lunch. We do have some options available for vegetarian, vegan, gluten-free, I think. I don't know if we've got everybody's dietary restrictions, but if you can't find what you need, check with one of our assistants outside, and hopefully we'll have something available for you. I'd like to start back up on our schedule on 12:45, but also, as I mentioned earlier, we've got some great sponsors. They've got tables set up, so I encourage you to please visit the sponsor booth during our lunch break as well. And we'll see you back in here at 12:45. Back to you for another question we had online, I believe.
Okay, so the question is from Nigel Zing. Their testbed software is CFE-based, not CFS. Would it be difficult to integrate with SBN Proto better?
Yeah, so the SBN, I'm not sure if that was one of the libraries that was listed that they're planning to do open release on. I don't think that is, right? SBN?
SBN and Proto-Better is planned for.
Right, but it's not out there right now, right?
It's not out there right now, but so at this point right now, I think you'd need like a Space Act agreement or some kind of arrangement with NASA for now, but it is planned. It is planned. Yeah.
Okay, thank you.